Imagine looking up at the night sky and realizing that every single point of light you see, every star, every galaxy, has a beginning. But what if I told you that there was a time before stars, a period of complete darkness that lasted for millions of years after the birth of our universe? This is where our journey begins, not with what we see, but with what we count the mysterious era when the very first stars and galaxies ignited, forever changing the cosmos. These ancient celestial bodies hold secrets that challenge everything we think we know about space, time, and our own origins. Today, we're going to explore 30 of the most captivating mysteries surrounding these cosmic pioneers, questions that even the most brilliant minds in astrophysics are still racing to answer. Think about it, the first stars were unlike anything that exists today. They were colossal, blazing with intense energy, and made of nothing but hydrogen and helium. They lived fast and died young, seeding the universe with the elements that would one day form planets, oceans, and even us. Yet, despite their profound importance, we've never directly seen one. They remain hidden in the deepest reaches of time and space, their light so faint and stretched by the expansion of the universe that our most powerful telescopes are only just beginning to catch glimpses of their echoes. How did these giants form? What did they look like? And what triggered the transition from a dark, empty cosmos to one filled with light and structure? These aren't just academic questions, they're fundamental to understanding our place in the universe. Together, we'll travel back over 13 billion years to an era so remote it defies imagination. We'll tackle mysteries ranging from the nature of dark matter's role in building the earliest galaxies to the cataclysmic deaths of the first stars that may have given rise to the supermassive black holes we observe today. This is a story of cosmic evolution, of how emptiness gave way to complexity, and how each discovery brings us closer to unraveling the grand narrative of existence itself. So settle in and open your mind. We're about to dive into the enigmas that shaped everything and the thrilling quest to shed light on the universe's oldest secrets. Our first great mystery takes us to the very beginning of this story, to a period so profoundly empty and silent it's almost impossible to conceive. We call it the Cosmic Dark Ages. Picture the universe just moments after the Big Bang, a seething, expanding cloud of hot, dense plasma, so energetic that light particles, photons, were trapped in a constant dance with electrons bouncing off them endlessly. There was no light, no structure, just a brilliant, impenetrable fog. But as the universe continued to expand and cool, something monumental happened. Roughly 380,000 years after the Big Bang, the temperature dropped enough for electrons to finally be captured by protons, forming the very first atom's neutral hydrogen. And in that instant, the fog lifted, the photons suddenly set free, streamed across the universe. We see that released light today as the cosmic microwave background, the oldest picture we have of everything. But then, something extraordinary occurred. Silence. The universe went dark. With no stars, no galaxies, and no new sources of light, the cosmos entered a profound and deeply mysterious chapter that would last for hundreds of millions of years. This is the true cosmic dark ages. It wasn't just an absence of light, it was an era of profound quiet and anticipation. The universe was filled with this neutral hydrogen gas, a vast, featureless sea stretching in every direction. Yet, beneath this serene surface, invisible forces were at work. Tiny, random fluctuations in density, imprints left over from the universe's violent birth, were starting to get a gravitational assist. The mysterious gravitational pull of dark matter, which makes up most of the universe's mass, began to act like a cosmic scaffolding. It started to gently tug on these pockets of slightly denser gas, pulling them together with agonizing slowness over millions of years. We have no direct observations of this era. It is, by definition, dark. Our most powerful telescopes cannot see back this far because there was no light to see. It's a blind spot in our cosmic timeline, a chapter missing from our history books. So how do we even begin to understand it? We rely on brilliant theoretical models and computer simulations to paint a picture of this hidden time. They suggest that within these vast, dark hydrogen clouds, the first structures were slowly, quietly taking shape. Vast filaments of dark matter formed a colossal web across the expanding universe, and along these invisible threads, ordinary matter began to flow, pooling into deeper and deeper gravitational wells. These were the seeds of everything to come, the first proto-galaxies, the nurseries where the very first stars would eventually be born. This was the universe preparing for its greatest act, the dawn of light, which would bring an end to the darkness and ignite the cosmos for the very first time. And from that profound cosmic silence, the darkness finally gave way to light. The immense gravitational wells that had been gathering neutral hydrogen for millions of years reached a critical tipping point. Deep within these primordial nurseries, pockets of gas collapsed under their own weight, heating up to incredible temperatures until nuclear fusion sparked in their cores. This was the moment of first light, the birth of the very first stars. But these weren't just any stars. Astronomers call them population 3 stars, and they were likely the most extraordinary and alien objects the universe has ever created. Unlike the stars we see today, which are enriched with heavy elements from previous generations, these pioneers formed from the pristine, elemental soup left over from the Big Bang, a pure mixture of only hydrogen and helium. This fundamental lack of heavier elements meant their formation process was entirely different, a fact that leads us to the heart of this second great mystery. Without elements like carbon or oxygen to help radiate heat away, the collapsing clouds of gas couldn't fragment into smaller clumps as easily. The physics of this pristine environment suggests that these stars could have grown to absolutely monstrous sizes before triggering fusion. We're talking about behemoths potentially between 100 and 1,000 times the mass of our Sun. To put that in perspective, if one of these stars were placed at the center of our solar system, its surface might extend beyond the orbit of Jupiter. These colossal entities would have lived ferociously brilliant but tragically short lives, burning their nuclear fuel at a breathtaking rate to support their immense mass. They would have shone with a fierce, blue-white intensity millions of times brighter than our Sun, only to explode in spectacular supernova after just a few million years, a mere blink in cosmic time. Their cataclysmic deaths were just as important as their births. In their final moments, these giant stars forged the first heavy elements in the universe, the carbon, oxygen, iron, and all the other elements essential for rocky planets and life itself. They quite literally seeded the void with the building blocks of future complexity. This is why finding direct evidence of a population 3 star is considered the holy grail of modern astronomy. It would be like finding the missing link in the cosmic evolutionary chain, but this is an incredibly difficult hunt. Their great distance means their light is exceedingly faint, and the expansion of the universe has stretched it far into the infrared part of the spectrum, beyond what our eyes can see. We are on the cusp, however. The James Webb Space Telescope, with its unprecedented infrared sensitivity, is designed to peer back into this era, searching for the unique chemical fingerprint of a star that lived and died before the universe was ever polluted with metals. Finding one would confirm a fundamental pillar of our cosmic history and give us a glimpse of the majestic, violent giants that ended the Dark Ages and illuminated the cosmos for the very first time. So the first stars did more than just end the darkness. They began a second, even more profound transformation of the entire cosmos, an event we call the epoch of reionization. Imagine the universe at that point, no longer in the Dark Ages, but not yet the transparent expanse we know today. It was still filled with that vast sea of neutral hydrogen gas, and while this gas is transparent to visible light today, it wasn't back then. To the high-energy, ultraviolet light pouring off those first massive stars, that neutral hydrogen was like a thick, pervasive fog. A photon of UV light leaving one of these brilliant new stars wouldn't get very far before it was absorbed by a neutral hydrogen atom. This would knock the atom's electron loose, briefly ionizing it, but that electron would soon be recaptured by another proton, resetting the cycle. The universe on the largest scales was still largely opaque to this specific, critical type of light. But those first stars were so incredibly powerful and numerous that they began to change this reality. They acted like countless tiny ultraviolet lamps, each working to burn away the fog in their immediate vicinity. Over hundreds of millions of years, these individual bubbles of ionized hydrogen, known as Stromgren spheres, began to grow and eventually overlap. It was a slow, relentless process, a cosmic battle between light and matter where the first galaxies and quasars joined the fray, their intense radiation pouring out into the voids. This was the reionization era, the universal transition from a neutral state to a fully ionized one, where the fog was permanently lifted and the universe became transparent to ultraviolet light just as it is today. This transparency is the reason we can see so far back in time. Without it, the light from distant galaxies would be absorbed long before it ever reached our telescopes. The profound mystery, however, lies in the how and the when. We know reionization was completed by around the time the universe was 1 billion years old, but its precise timeline and the primary drivers behind it are subjects of intense debate. Was it predominantly the work of those massive population 3 stars, or did early galaxies with their collective power play the leading role? Perhaps the radiation from the first supermassive black holes, the quasars, provided the final critical push. Each of these sources would have created a different pattern and pace of reionization. The challenge for astronomers is that this process didn't happen uniformly. It was a patchy, chaotic process, with some regions clearing early and others holding out for much longer. We are essentially trying to piece together the history of this cosmic clearing by studying its final effects on the light that travels to us from the most distant quasars and galaxies. As we observe these ancient objects, we see telltale signs in their spectra-specific absorption lines known as the Gunn-Peterson trough that tell us how much neutral hydrogen their light had to travel through, allowing us to map the end stages of this universal transformation. Unraveling the details of reionization is key to understanding the full life cycle of the first luminous objects and how they fundamentally reshaped the cosmos to make it the recognizable, observable universe we study today. But if the first stars were the pioneers, then the first black holes were the enigmatic architects that followed, shaping the cosmos in ways we are only beginning to comprehend. This brings us to our fourth great mystery, a true cosmic chicken or egg dilemma that challenges our understanding of structure formation itself. Which came first, the galaxy or the black hole? For a long time, the prevailing theory was a logical sequence. First, gas collapses to form the first stars and protogalaxies. Then, the most massive of these stars die in supernova, leaving behind stellar mass black holes. These small black holes could then merge or accrete gas over billions of years, gradually growing into the supermassive monsters we find at the centers of galaxies today. It's a clean, orderly timeline, but the universe, it seems, loves to defy our neat expectations. Our observations have thrown a monumental wrench into this idea. We've discovered fully formed supermassive black holes with masses exceeding 1 billion suns, existing when the universe was less than 700 million years old, a mere 5% of its current age. For a black hole to grow that massive that quickly, it faces a serious problem known as the Eddington limit. This is a fundamental law of physics that dictates how fast a black hole can devour matter. If it eats too greedily, the intense radiation from the infalling material actually pushes away the surrounding gas, effectively putting the brakes on its own growth. To reach 1 billion solar masses so early, a black hole would have to consistently feed at or very near this maximum theoretical rate for its entire existence, which is incredibly difficult to sustain. It's like needing to win every single race you ever run, from toddler to Olympian, without ever slowing down. This has led many scientists to propose a radical alternative. Perhaps these black holes didn't grow from stars at all. Maybe they were born big. This is the concept of primordial black holes. The idea is that in the incredibly dense, chaotic conditions just moments after the Big Bang, random fluctuations in density could have been so extreme that pockets of space directly collapsed into black holes. These wouldn't be the stellar gravestones we know today. They would be primordial entities. Their masses could range from tiny, asteroid-sized objects to colossal ones weighing thousands of suns. If such behemoths formed, they would have been present from the very beginning, providing ready-made seeds for the supermassive black holes we see. In this scenario, the very first galaxies might not have formed on their own. Instead, they could have assembled directly around these pre-existing gravitational anchors. A primordial black hole would act as a cosmic nucleus, its immense pull attracting vast clouds of dark matter and gas, catalyzing the birth of a galaxy around it. The black hole wouldn't be a resident of the galaxy, it would be its reason for being. On the other side of the debate, the traditional model still has compelling arguments. Perhaps the first stars were even more massive than we think, leaving behind larger, heavy seeds. Or maybe the early universe provided perfect conditions for rapid, sustained growth, with dense, cold gas flows funneling directly into the center of young protogalaxies, allowing black holes to feast in a way that is impossible in the quieter universe of today. The truth might even be a combination of both paths. The James Webb Space Telescope is now peering into this critical era, searching for the faint signatures of these first black holes and their host galaxies. By measuring their masses and comparing their growth rates, we hope to finally solve this puzzle. Did galaxies give birth to their central black holes, or did black holes act as the seeds around which galaxies themselves were built? The answer will rewrite the story of how all structure, including our own Milky Way, came to be. Yet even as we ponder the origins of black holes and galaxies, a more fundamental question emerges from the cosmic dawn. When did this grand construction project actually begin? This leads us to a fifth and deeply puzzling mystery: the precise timing of the first galaxies. If we think of the universe's history as a feature-length film, we've just watched the opening credits, the Big Bang, and the release of the cosmic microwave background. Then the screen goes dark for the long cosmic dark ages. But when does the first scene of galactic construction finally flicker to life? The answer is far from settled, and different lines of evidence are telling us conflicting stories, suggesting that the universe's earliest chapters might be more complex than we ever imagined. On one side, we have our most sophisticated computer simulations of cosmic evolution. These virtual universes, running on some of the world's most powerful supercomputers, are built upon the well-tested laws of physics and our standard model of cosmology. They consistently point to a universe that took its time. In these digital recreations, the first recognizable protogalaxies, gravitationally bound structures of dark matter, gas, and the first stars, don't really begin to assemble until the universe is at least 100 to 200 million years old. This timeline allows for the gradual, slow gravitational collapse mandated by the presence of dark matter. The invisible scaffolding needs time to form, and the gas needs time to flow along it, cool, and eventually fragment into stars. It's a stately, deliberate process of cosmic architecture. However, astronomy is driven by observation, and what we're beginning to see with powerful new telescopes is challenging this patient timeline. The James Webb Space Telescope, in particular, has been staring deep into the past and finding an astonishing number of surprisingly bright, massive, and evolved galaxies at extremely high redshifts, meaning they exist at a time when the universe was only 200 to 300 million years old. Finding galaxies at this epoch isn't the surprise. Finding them to be so large and so fully formed is the shock. It's like discovering photographs of a bustling, modern city taken just a few decades after the founding of its first settlement. These galaxies appear to have been under construction for much longer than our models allow, suggesting that the first seeds of galaxy formation may have been sown extraordinarily early, perhaps only tens of millions of years after the Big Bang. This creates a significant tension between theory and observation. How could galaxies grow so big so fast? One possibility is that our understanding of the very first stars is incomplete. Perhaps population 3 stars were even more efficient at producing light and expelling material through powerful winds, which would have heated the surrounding gas and actually slowed down later star formation. Alternatively, maybe the early universe provided conditions we haven't fully accounted for, such as more pronounced dark matter clumps or unique gas chemistry, that allowed for a much more rapid, explosive start to galactic assembly. Another fascinating idea is that our standard model of cosmology itself, the lambda-cold dark matter model, might need a slight tweak when applied to these extreme environments, though this is considered a more radical proposition. The challenge in resolving this mystery lies in the difficulty of the observations themselves. When we look at these most distant galaxies, we are not seeing them as they are. We are seeing them as they were, their light incredibly faint and stretched into the infrared. Measuring their precise age and mass is an enormous technical challenge. Astronomers have to analyze the galaxy's spectrum, the breakdown of its light into different colors to look for specific signatures. One key signal is the Lyman break, a telltale drop in intensity caused by the absorption of light by neutral hydrogen. The position of this break in the spectrum tells us the galaxy's redshift and thus its distance and age. But to understand its mass and maturity, we need to look at subtler features, which requires collecting every precious photon we can. Different observational techniques can also point to different timelines. Studies of the cosmic microwave background polarization give us one estimate for when the first large-scale structures began to form. The patterns of absorption lines in the spectra of even more distant quasars, which act as cosmic lighthouses shining through the fog of neutral hydrogen, provide another. And the properties of the galaxies we directly detect offer a third. Reconciling these different clocks is one of the most active and exciting areas of cosmology today. Each new deep field image from Webb pushes the potential timeline for galaxy formation further back, forcing us to re-examine our most fundamental ideas about how our universe emerged from darkness and began building the magnificent structures we see today. Yet for all the gravitational pull of dark matter, it was the ordinary matter, the gas, that had to take the final, critical step to form a star. This is where the mystery truly deepens. Dark matter, as far as we understand it, doesn't interact with light or with itself. It simply provides the gravitational well. The ordinary gas, however, can radiate energy away. To collapse all the way down into a dense star-forming core, this hydrogen and helium gas needs to cool. In the modern universe, gas clouds cool efficiently through heavy elements like carbon and oxygen, which emit light as they are excited. But in the pristine early universe, those elements didn't exist yet. So how did the first gas clouds cool enough to fragment into stars? The primary theory points to molecular hydrogen. Trace amounts of hydrogen molecules forming in the cloud could have emitted just enough infrared radiation through a specific rotational transition to allow the gas to lose heat and continue its collapse. This process is incredibly fragile and inefficient compared to modern cooling methods. It suggests that the first stars could only form in the very deepest, most massive dark matter halos, where the gravitational forces were strong enough to overcome the limited cooling. This intimate, step-by-step dance between the invisible scaffolding of dark matter and the physical behavior of ordinary gas is what ultimately dictated when, where, and how the universe's first light switched on. Understanding the precise properties of dark matter is therefore not just an abstract pursuit. It is the key to unlocking the story of our own cosmic origins. The mass, the clumpiness, and the potential interactions of dark matter particles would have directly controlled the formation of those first halos and, by extension, the entire timeline of cosmic dawn. This journey into the earliest structures of the universe leads us directly to a mystery that challenges our understanding of dark matter itself, a puzzle known as the missing satellites problem. Our most successful model of the cosmos, the lambda-cold dark matter model, is brilliant at predicting the large-scale structure of the universe, the vast cosmic web of filaments and voids that we observe. When we run supercomputer simulations based on this model, they paint a very specific picture of how the first galaxies assembled. They show that a large galaxy, like our own Milky Way, didn't form in isolation. It should have been built up over time through the mergers and accretion of hundreds, even thousands of smaller protogalaxies. These are the building blocks, the cosmic bricks. And according to the physics in these simulations, the dark matter halos that hosted these small building blocks shouldn't have disappeared. They should have survived as a vast swarm of satellite galaxies, each a small cluster of stars bound together by its own dense knot of dark matter, orbiting the larger primary galaxy like bees around a hive. The problem is stark and simple. We don't see them. Our simulations predict that there should be orders of magnitude more small, faint dwarf galaxies orbiting large galaxies than we actually observe with our telescopes. For every one we find, the models say there should be 100. It's as if we had a theoretical blueprint for a grand castle, specifying that it must be constructed from 10,000 bricks, but when we go to the site, we only find 100 bricks lying around. The foundation is there, the castle stands, but the majority of its building materials are missing. This isn't just a minor accounting error. It's a fundamental discrepancy that forces us to question either our understanding of dark matter or our grasp of the physics that govern the earliest, smallest galaxies. So where did all these satellites go? Astrophysicists have proposed several compelling solutions. One leading idea is that our theories are correct about the dark matter, that all those small halos do exist, but our assumptions about star formation within them are wrong. Perhaps the vast majority of these small dark matter clumps never managed to light up with stars at all, rendering them invisible to our telescopes. Why might that be? The process of star formation is delicate. After the first stars exploded, they flooded the universe with intense ultraviolet radiation and powerful supernova shocks. This cosmic feedback could have heated the gas within these tiny potential galaxies, making it too hot and energetic to collapse and form stars. Or it could have physically blown the gas right out of these shallow gravitational wells entirely, leaving them starved and dark. In this scenario, the universe is filled with these invisible, dark galaxies, pure dark matter halos with no stars to mark their location. We wouldn't see them, but their gravitational influence would still be there. Another possibility is that we simply haven't found them yet because they are incredibly faint. Modern sky surveys are discovering more and more ultra-faint dwarf galaxies, and their numbers are increasing as our technology improves. The Vera C. Rubin Observatory, set to begin operations soon, is specifically designed to detect these incredibly dim objects. It's possible we are on the verge of finding a whole new population of satellites that have been hiding in plain sight, which would go a long way toward closing the gap between theory and observation. However, a more radical solution suggests the problem isn't with the gas or our observations, but with the very nature of dark matter. The standard model assumes cold dark matter, meaning the particles move slowly and clump together easily, readily forming all these small-scale structures. But what if dark matter isn't cold but slightly warm? Warm dark matter would consist of lighter, faster-moving particles. This would suppress the formation of structure on the smallest scales. These faster particles would smooth out the smallest density fluctuations, preventing the very smallest dark matter halos from ever forming in the first place. In a warm dark matter universe, the missing satellites problem wouldn't exist because the theory would never predict thousands of tiny halos to begin with. The debate between cold and warm dark matter is a central one in cosmology, and the answer to the missing satellites could be a key piece of evidence pointing toward a deeper truth about the dominant yet invisible component of our universe. But these monumental stellar explosions were more than just brilliant finales. They were the universe's first and most important factories. Within their unimaginably violent conditions, a frenetic process of nucleosynthesis occurred, creating entirely new atomic nuclei. The incredible temperatures and pressures during the supernova event allowed for the rapid capture of neutrons, building upon the helium cores to forge elements like carbon, oxygen, neon, and iron in a matter of seconds. This was the birth of the first metals, a term astronomers use for any element heavier than helium. In a single cataclysmic flash, a star that began its life from a pure hydrogen and helium cloud was now seeding the void with the very ingredients for future planets, oceans, and life. The distribution mechanism was just as important as the creation. The supernova shockwave acted like a cosmic shotgun blast, violently ejecting these newly forged elements at tremendous speeds, hurling them far out into the surrounding pristine gas of the early universe. This process wasn't uniform or tidy. The nature of the explosion and the elements it produced depended entirely on the mass of the progenitor star. The most massive behemoths might have collapsed directly into black holes, potentially locking away their heavy elements forever if the explosion failed to materialize. Others would have died in particularly energetic pair instability supernova, events so powerful they would completely obliterate the star, leaving no remnant behind and scattering their entire enriched contents far and wide. The specific mix of elements each supernova contributed, its chemical fingerprint became the inheritance for the next generation of stars and planets. This leads to one of the great forensic challenges in astronomy. We are now searching for that second generation of stars, the ones that formed from gas clouds lightly sprinkled with the ashes of the very first supernova. These ancient stars, known as extremely metal-poor stars, are like cosmic time capsules. By analyzing their atmospheres with powerful spectrographs, we can dissect the precise elemental abundances they contain, looking for the unique signature of enrichment from a single, first-generation supernova. Finding such a star would be like finding a preserved recipe from the universe's first kitchen. The profound mystery, however, lies in the speed and efficiency of this enrichment. Our observations show that the universe transitioned from a pristine state to one with a detectable level of metals surprisingly quickly. We find evidence of enriched gas less than 1 billion years after the Big Bang. How did these first heavy elements, scattered by isolated supernova in a vast and expanding cosmos, get mixed so thoroughly into the interstellar medium? The sheer scale seems daunting. One supernova, even a tremendously powerful one, can only pollute a localized bubble of space. For the universe to become globally enriched, these bubbles needed to overlap and merge, a process that requires either an astonishingly high rate of first star deaths or a highly effective mechanism for transporting metals across great distances. Some theories suggest that powerful galactic winds, driven by the collective energy of many supernovae within a young protogalaxy, could have vented enriched material out into intergalactic space. Others point to the role of early supermassive black holes and quasars, whose intense radiation and jets could have stirred the cosmic pot on a truly colossal scale. Unraveling this mystery is key to understanding our own existence, for it tells the story of how the raw materials for everything we see and are, the iron in our blood, the calcium in our bones, the silicon in our planet, were forged in the hearts of those first long-dead stars and then scattered across the cosmos, waiting for their chance to become part of us. This brings us to a profound and paradoxical force that began to shape the cosmos almost immediately after the first stars blinked into existence, the explosive feedback from the first supernova. Think of these stellar explosions not just as endings, but as powerful regulatory mechanisms. They were the universe's first tools for self-regulation, creating a complex feedback loop that could both give life and take it away on a galactic scale. The death of one generation of stars held the power to dictate the fate of the next, and understanding this push and pull is key to unraveling why galaxies look the way they do. On one hand, a supernova's shockwave can be the ultimate catalyst for new star birth. Picture a vast, relatively quiet cloud of primordial gas. It might be on the verge of collapse but needs a nudge. When a supernova shockwave slams into such a cloud, it doesn't just gently compress it. It violently squeezes it, creating intense ripples and regions. OF Chinese letter, Chinese letter, Chinese letter, Chinese letter. This sudden increase in pressure can overcome the cloud's internal support mechanisms, like turbulence or magnetic fields, triggering a gravitational collapse that might never have happened otherwise. It's like a cosmic domino effect where a single stellar death can set off a chain reaction of new births in its vicinity. This positive feedback is thought to be a primary driver of star formation in the modern universe, and it likely played a crucial role in the early cosmos as well, helping to rapidly populate the first protogalaxies with successive generations of stars. Yet, this creative force has an equally powerful destructive counterpart. The same unimaginable energy that can compress a gas cloud can also utterly destroy it. If a supernova shockwave is too powerful, or if it hits a cloud that isn't sufficiently dense, it won't compress it, it will shred it. The cloud can be torn apart, its gas heated to millions of degrees and blown clear out of the shallow gravitational well of its nascent galaxy. This process, known as galactic outflows or winds, represents negative feedback. It effectively shuts down star formation by removing the very fuel required to make new stars. In the fragile early galaxies, which had relatively weak gravity, a few powerful supernovae could have had a catastrophic impact, potentially sterilizing entire dwarf galaxies by ejecting their gas reservoirs into intergalactic space, leaving behind a dark, starless halo of dark matter. The ultimate outcome for any given region of space depended on a delicate and chaotic balance of factors: the mass and energy of the supernova, the density and structure of the surrounding gas, and the gravitational strength of the host dark matter halo all played a role. A very massive halo could hold onto its gas despite the explosions, leading to sustained star formation. A smaller halo might see its star-forming career cut tragically short. This feedback process is why supercomputer simulations of galaxy formation are so complex. Getting the recipe right for how much gas is turned into stars versus how much is blown away is one of the biggest challenges in modern astrophysics. The echoes of these first explosions literally set the efficiency of star formation for all future generations, determining the final mass and appearance of galaxies, including our own Milky Way. It was a cosmic trial by fire, where the violent deaths of the first stars decided which galactic seeds would flourish and which would fade back into darkness. Now, if we could somehow travel back and observe the universe just a few 100 million years after the Big Bang, the night sky would look nothing like the one we see today. Instead of the majestic, well-ordered spirals and smooth ellipticals that define our modern cosmos, we would find ourselves surrounded by a chaotic menagerie of bizarre shapes, clumpy, irregular, and tumultuous structures that seem to defy any clear classification. This is the great mystery of galaxy morphology evolution. Why did these early systems look so profoundly different, and what cosmic forces sculpted them over billions of years into the familiar forms we recognize now? The answer lies in understanding that the early universe was a far more violent and dynamic place, a cosmic frontier where the rules of structure formation were being written in real time. The primary difference boils down to a simple concept: stability, or rather, the lack of it. Modern spiral galaxies like our Milky Way are remarkably stable systems. Their beautiful, rotating disks are governed by a delicate balance between gravity, which pulls matter inward, and centrifugal force from their rotation, which holds it out. This equilibrium allows for orderly, long-lived structures like spiral arms, but in the early universe, this balance had not yet been achieved. The first proto-galaxies were forming within a much denser, more chaotic environment. They were constantly being bombarded by torrents of cold gas flowing in along the filaments of the cosmic web, and they were frequently merging with other small proto-galaxies. These violent interactions injected enormous amounts of energy and angular momentum, preventing the system from settling down into a calm, rotating disk. Instead of a smooth structure, you got a tumultuous, clumpy mess. Imagine trying to form a smooth, flat disk of pizza dough by constantly throwing in new handfuls of flour and globs of water, while simultaneously smashing another ball of dough into it every few minutes. The result would be a lumpy, irregular, and chaotic blob. That's essentially what was happening to these baby galaxies. The gas within them didn't collapse into a neat disk, it fragmented into massive, dense knots. Each of these knots was a powerhouse, a region furiously forming massive stars. To a distant observer, these early galaxies wouldn't look like a unified single object, but rather like a string of brilliant pearls, a collection of ultra-luminous clumps shining with the fierce blue-white light of hot, young stars. These are what astronomers call clump clusters or chain galaxies, and they are the dominant morphology in the early universe. The transition from this chaotic state to the ordered galaxies we see today was a slow process driven by two key mechanisms. The first is the gradual settling of the system. Over hundreds of millions of years, the constant bombardment from mergers and gas accretion slowed down. Within the galaxy itself, dynamical friction began to work its magic. The massive star-forming clumps, being so dense, interacted gravitationally with the surrounding dark matter and stars. This caused them to lose energy and momentum, slowly migrating inward through the galaxy. Many of these clumps likely merged in the center, piling up to form the very first galactic bulges, the dense, central cores of stars we see at the heart of most spirals. This inward migration of clumps is a crucial step in building a galaxy's central structure. The second major factor was the emergence of a stabilizing component, a massive dark matter halo. As a galaxy grew through mergers, it became enveloped by an increasingly large and massive halo of dark matter. This halo isn't just a passive backdrop, it plays an active role in shaping the galaxy it hosts. A massive, extended dark matter halo provides a deep, smooth gravitational potential well. This helps to stabilize the gas within the galaxy against the violent perturbations that cause fragmentation and clumping. It acts like a cosmic shock absorber, damping out the chaos and allowing the ordinary matter to settle into a more orderly, rotating disk. The presence of a supermassive black hole at the center, growing alongside the bulge, also contributes to this stabilization through its own powerful gravitational influence and the energetic feedback from its accretion, which can regulate gas flow and prevent renewed fragmentation. So the evolution of galaxy morphology is a story of the universe maturing. It's the journey from a violent, chaotic, and gas-rich youth to a more settled, stable, and orderly adulthood. The strange, clumpy galaxies we see with the James Webb Space Telescope are not broken or anomalous. They are cosmic infants caught in the act of assembly, showing us the raw and tumultuous processes that eventually, over billions of years, gave rise to the majestic and beautiful galaxies we call home. Yet, even as we map the chaotic shapes of the first galaxies, our telescopes have revealed something else lurking in the deep fields of the early universe, something far larger and more enigmatic. Scattered across the cosmic dawn are colossal, faintly glowing clouds of gas, each one spanning a scale that defies belief, often larger than the Milky Way itself. These are the Lyman alpha blobs, and they represent one of the most puzzling structures we've ever found. Their name comes from the specific type of light they emit, a wavelength known as Lyman alpha radiation, which is produced when electrons within hydrogen atoms drop to their lowest energy state. To detect one is to see a vast, diffuse nebula glowing with this unique light, but the sheer size and brightness of these blobs present a profound mystery. What on Earth, or rather in the cosmos, could possibly be energizing such immense structures? The discovery of these blobs was almost accidental. Astronomers using large telescopes would sometimes detect these enormous, fuzzy patches of Lyman alpha emission in their deep field images. They weren't compact like galaxies or quasars. They were extended, amorphous, and hauntingly beautiful. Some of the largest blobs can stretch over 300,000 light-years across. To power such a vast glow requires a tremendous source of energy, but when astronomers looked toward the center of these blobs, they often found nothing obvious. No brilliant quasar, no ultra-luminous galaxy that could account for the radiation. It was as if we were seeing the ghostly glow of a city from a distance, but upon arriving, finding the streets completely dark and deserted, with no clear source for the light. This has led to a fascinating detective story with several compelling suspects. One leading theory points to intense bursts of star formation happening within galaxies hidden deep inside the blob. In this scenario, the prodigious amount of ultraviolet light from millions of hot, young, massive stars ionizes the surrounding hydrogen gas. When those atoms reassemble and their electrons cascade back down to their ground state, they release that energy as Lyman alpha photons. But because the gas cloud is so enormous and dense, the photons don't just escape directly. They undergo a process called resonant scattering, bouncing from atom to atom like a pinball in a machine, which can make the cloud glow uniformly across its entire vast extent. This would make a Lyman alpha blob the ultimate signpost for a colossal stellar nursery, a galaxy undergoing a literal firestorm of star birth on a scale we rarely see in the local universe. Another compelling hypothesis involves the dark matter scaffolding of the cosmos. These blobs are often found at the intersections of the cosmic web, where vast filaments of dark matter meet. As enormous amounts of pristine gas from the intergalactic medium funnels along these filaments and into the waiting gravitational well of a massive dark matter halo, it can release a tremendous amount of gravitational potential energy. This infalling gas heats up and can shock, potentially producing the conditions needed to excite the hydrogen and cause it to glow. In this view, a Lyman alpha blob isn't primarily about star formation. It's a sign of a massive galaxy or protocluster in the act of assembly, its gravitational pull lighting up the very gas that is raining down to feed its growth. It would be a cosmic beacon marking the site of a massive construction project. A third, more extreme possibility involves the most energetic objects in the universe, active supermassive black holes. Perhaps a quasar, buried deep within the heart of the gas cloud, is pumping out immense amounts of energy. Its intense radiation could be ionizing the surrounding hydrogen, while its powerful jets might be heating the gas even further, causing the entire structure to fluoresce. The central engine might be so enshrouded in dust and gas that its direct light is obscured, leaving only the eerie, pervasive glow of the illuminated blob as evidence of its hidden power. The truth is, there is likely no single explanation that fits every blob. These enormous structures probably represent different phases or types of cosmic activity. Some might be powered by starbursts, others by gas accretion, and still others by hidden quasars. The key to solving the mystery lies in looking beyond the Lyman alpha light itself. Modern observatories like the James Webb Space Telescope are now studying these blobs at other wavelengths, searching for the infrared signatures of warm dust or the specific emission lines from other elements that would betray the presence of intense star formation or a hidden black hole. Each blob is a fossilized snapshot of the extreme processes that shaped the early universe, and by deciphering their power source, we learn not just about the blobs themselves, but about the fundamental forces that built the cosmic structures we inhabit today. But as we push our observational tools to their absolute limits in the hunt for these first flickers of light, we enter a realm where the signals are incredibly faint and the potential for error is enormous. This brings us to one of the most electrifying and contentious mysteries in modern cosmology, the hunt for a definitive signal from the cosmic dawn itself, and the fierce debate surrounding a claimed detection that, if true, would force us to rewrite our fundamental understanding of the universe's first chapters. It's a story that centers on a seemingly mundane number, 21 centimeters. This is the wavelength of light emitted by neutral hydrogen atoms, the most abundant substance in the early universe, and it provides a potential window into the era of the first stars. The logic is beautifully simple. Before the first stars ignited, the vast sea of neutral hydrogen gas would have been absorbing energy from the even more ancient cosmic microwave background, making it appear cold against the backdrop of space. But when those first massive stars switched on, their intense ultraviolet light would have excited that hydrogen, heating it up and causing it to emit its own faint radio signal at that 21-centimeter wavelength. By the time this incredibly ancient light reaches us, the expansion of the universe has stretched it out to meters-long wavelengths, placing it in the range of radio telescopes. In 2018, a small and highly specialized radio antenna experiment in the remote deserts of Western Australia, called EDGES, made an announcement that sent shockwaves through the astrophysics community. After years of painstaking data collection and analysis designed to filter out every possible source of terrestrial interference, the team reported they had detected this very signal, a deep dip in the radio spectrum that matched the predicted fingerprint of hydrogen interacting with the first starlight. The detection itself was a monumental technical achievement, but the real bombshell was the shape and depth of that dip. It was far more pronounced than any leading theory had predicted. According to the EDGES data, the ancient hydrogen gas appeared to be much colder than our standard models of cosmology said it should have been. For the gas to be that cold, something must have been siphoning away its heat with astonishing efficiency in the early universe, a phenomenon for which we have no ready explanation. This is where the controversy ignites. The proposed explanations for this anomalous cooling are as radical as the finding itself. The most discussed theory involves an interaction between the normal hydrogen gas and the mysterious dark matter that permeates the cosmos. If dark matter particles have even a tiny amount of interaction with normal matter, far beyond the simple gravitational pull we assume, they could have acted as a cosmic coolant, drawing heat away from the hydrogen gas and allowing it to reach the profoundly low temperatures suggested by the EDGES data. This would be a revolutionary discovery, providing our first ever clue about the physical nature of dark matter beyond its gravity. However, many physicists are deeply skeptical, as this would require a type of dark matter particle that doesn't fit neatly into our existing theoretical frameworks. The other major possibility, and the one many scientists consider more likely, is that the signal isn't cosmic at all. Detecting this faint whisper from the dawn of time is like trying to hear a single pin drop in a roaring hurricane. The challenge of eliminating all terrestrial radio interference, from FM radio stations to satellite transmissions, is immense. Even more pernicious are systematic errors within the instrument itself. The EDGES antenna sits on the ground, and its measurements could be subtly corrupted by the complex ways radio waves interact with the soil beneath it. Since the initial announcement, numerous teams have published papers suggesting that the claimed signal could be entirely explained by such instrumental effects or by inadequate modeling of the foreground noise from our own galaxy. The debate remains utterly unresolved, a testament to the extreme difficulty of doing 21-centimeter cosmology. New experiments like SARA's in India and LEDA in the United States have been conducting their own independent searches. Some have reported not finding the signal, further fueling the doubt, though the specific details of each experiment mean the case is not yet closed. The implications of this mystery stretch far beyond a simple academic disagreement. A confirmed detection of the edge's signal would be nothing short of a paradigm shift, forcing a dramatic revision of our understanding of particle physics, dark matter, and the thermal history of the early universe. It would be direct, observational evidence that we are missing a fundamental piece of the cosmic puzzle. On the other hand, if the signal is ultimately proven to be an artifact of the instrument, it remains a powerful lesson in the painstaking rigor required to explore the farthest frontiers of science. The pursuit continues, with next-generation telescopes like the Square Kilometre Array being designed specifically to cut through this controversy and finally capture the true song of the cosmic dawn, whatever it may be. Tucked away in the vast gravitational embrace of galaxies like our own Milky Way, we find the most unassuming and enigmatic of cosmic relics, the ultra-faint dwarf galaxies. These are not the brilliant spiral whirlpools or glowing elliptical clouds we typically picture. Instead, they are incredibly dim, diffuse collections of stars so sparse that if you were standing on a planet within one, the night sky would appear nearly empty. Their total light output can be less than that of a single bright star in our own galaxy. Yet, despite their feeble appearance, these tiny galaxies may hold the most pristine, undisturbed record of the universe's infancy. They are not just small galaxies. Many astronomers believe they are living fossils, the surviving building blocks from which all larger galaxies were assembled, preserved in a near-original state for over 13 billion years. What makes these faint smudges of light so extraordinarily ancient? The answer lies in their stars. When astronomers point their spectrographs at these dwarfs, they find a stellar population that is almost exclusively old. These stars are overwhelmingly metal-poor, meaning they contain only trace amounts of elements heavier than hydrogen and helium. This is the definitive chemical signature of a star that formed very early in the universe's history, from gas that had been seeded by only 1 or 2 generations of supernova at most. In some of these dwarfs, we've found stars with iron abundances less than 1/10,000th that of our Sun. They are time capsules, their composition effectively frozen since the era of the first stars. This suggests these galaxies got an early start, forming their stars in a tremendous burst of activity during the cosmic dawn, and then something happened that caused them to shut down almost completely. They have been in a state of suspended animation for eons, their stellar populations simply aging without renewal. This leads to the central puzzle of these fossils. Why did they stop forming stars? They possess 2 key ingredients required for star birth: gas and immense reservoirs of dark matter. Their dark matter halos are, in fact, disproportionately massive compared to their visible stars, meaning they should have had more than enough gravitational pull to continue gathering gas and creating new stars for billions of years. And yet, they didn't. The prevailing theory points to that very first generation of stars as the culprit. The same feedback processes that regulated star formation in larger galaxies may have been utterly catastrophic for these smaller, more fragile structures. When the first massive stars within a proto-dwarf galaxy went supernova, their explosions would have released enough energy to overwhelm the galaxy's shallow gravitational well. The resulting powerful winds could have blown all of the remaining star-forming gas clean out into intergalactic space, a process known as galactic quenching. With their fuel supply emptied into the void, these galaxies were left starved, unable to form new generations. Their star-forming careers were brilliant, brief, and ended abruptly, leaving behind only their ancient stellar populations as a fossilized record of that first burst of cosmic creativity. Their survival for all this time is another facet of the mystery. As a small galaxy orbits a giant like the Milky Way, it experiences intense gravitational tidal forces that can literally pull it apart. The fact that we see so many of these ultra-faint dwarfs today suggests they are anchored by incredibly dense, robust cores of dark matter that have allowed them to withstand this cosmic tug of war for billions of years. Studying them is like doing cosmic archaeology. By mapping their current positions and motions, we can trace the assembly history of our own galaxy, as each dwarf represents a captured piece of the original construction material. The next generation of telescopes will probe these faint fossils in ever greater detail, searching for even older stellar populations and measuring their dark matter distributions with greater precision. In their faint, ancient light, we may finally find the unaltered chemical fingerprints of the very first supernova, offering us a direct glimpse into the forces that brought the cosmic dark ages to a close and lit the path toward the universe we know today. But perhaps the most spectacular and violent events in the early universe were not the deaths of stars, but the feeding frenzies of the monsters they left behind. This brings us to a mystery that stands as one of the most formidable puzzles in all of cosmology: the astonishingly rapid rise of the first quasars. These are not subtle, hidden objects. A quasar, or quasi-stellar object, is the incredibly luminous core of a distant galaxy, powered by a supermassive black hole in the midst of an unimaginable feast. As vast quantities of gas, dust, and even stars spiral down into the black hole's gravitational well, the material is compressed and heated to millions of degrees, blazing with a light that can outshine an entire galaxy of stars. They are the most persistently luminous objects in the universe. Our mystery begins with the sheer age of the most distant quasars we've discovered. We have now observed these cosmic beacons shining from a time when the universe was less than 700 million years old, a mere 5% of its current age. This alone is staggering, but the real shock comes when we calculate the mass of the black holes powering them. By measuring the speed of gas whirling around the central engine and applying the laws of gravity, astronomers can weigh these monsters. The numbers are mind-bending. The quasar known as J034 plus 0002, for instance, is powered by a black hole with a mass over 1.5 billion times that of our Sun. And it's doing this when the universe is only 690 million years old. Think about that for a moment. A billion solar mass black hole had to form from scratch in less time than it has taken for humanity to evolve from the first hominids. According to our standard understanding of black hole physics, this shouldn't be possible. This is the heart of the timing problem. A black hole grows by accreting matter, but it faces a fundamental speed limit known as the Eddington limit. If a black hole eats too greedily, the intense radiation pressure from the infalling material actually pushes away the surrounding gas cloud, shutting off its own food supply. It's a cosmic case of biting the hand that feeds you. To reach a billion solar masses so quickly, a black hole would have to consistently feed at its absolute maximum Eddington rate for its entire existence without a single pause. It's an incredibly difficult feat to sustain, like trying to win every single race you ever run from infancy to the Olympics without ever slowing for a breath. This has forced cosmologists to consider some truly radical alternatives to the standard model of gradual growth. One compelling idea is that the very first black holes weren't born from stars at all, but were instead heavy seeds. Perhaps the first generation of stars included true monsters, behemoths with masses of hundreds of thousands of suns that collapsed directly into massive black holes without the messy business of a supernova. These ready-made heavy seeds would give subsequent growth a colossal head start. Another, even more exotic proposal is the direct collapse model. In this scenario, a massive cloud of pristine hydrogen gas doesn't fragment into stars at all. Instead, it collapses as a single, monolithic entity directly into a black hole with a starting mass of tens of thousands of suns. For this to happen, the gas cloud must avoid cooling and fragmenting, which requires it to be bathed in a powerful external source of ultraviolet light that prevents molecular hydrogen from forming. The culprits could be a nearby, intense starburst galaxy or an even earlier quasar. its radiation essentially pressure cooking a neighboring gas cloud into forming a single, massive black hole seed instead of a cluster of stars. There's also the tantalizing possibility that the early universe simply provided a perfect all-you-can-eat buffet for growing black holes. In the dense, gas-rich environments of the first protogalaxies, the rules may have been different. Perhaps cold, dense streams of gas were able to flow directly into the central regions without forming a hot, bloated accretion disk, allowing for super-Eddington accretion in short, violent bursts. The black hole could have gorged itself in a series of spectacular feasts, far exceeding its theoretical limit for brief periods. The truth might be a combination of all these paths. The James Webb Space Telescope is now hunting for these first quasars and their host galaxies, not just to find them, but to take a precise cosmic census. By counting how many there are at different epochs and measuring their masses, we can begin to reverse engineer their growth history. Did they start with heavy seeds and grow steadily, or did they experience explosive, punctuated growth? The answer will not only solve a timing paradox, but will reveal the dominant mechanisms that govern the growth of the most powerful engines in the nascent universe, setting the stage for the evolution of galaxies for billions of years to come. This brings us to a dynamic and violent process that fundamentally shaped the early cosmos, the rate at which the first galaxies crashed into one another. If you could witness the universe during its first few billion years, you wouldn't see the stately, isolated island universes we often imagine. Instead, you'd be watching a cosmic demolition derby, a chaotic and crowded scene where collisions and mergers were not rare catastrophes but a regular part of galactic life. The question of exactly how often these mergers occurred, however, is a major point of contention, with different observational methods painting surprisingly different pictures of the early universe's social habits. To understand why, we need to consider the environment. The early universe was a much denser and more compact place. While it was expanding, the average distance between galaxies was significantly smaller than it is today. Furthermore, galaxies were forming along the dense filaments of the cosmic web, which funneled them toward massive intersections where dark matter halos were growing. In these crowded cosmic cities, close encounters and direct collisions were almost inevitable. Our standard cosmological models and sophisticated computer simulations strongly support this view, suggesting that major mergers, where two galaxies of roughly similar size combine, were a dominant driver of galaxy evolution, especially for the most massive systems. These violent interactions could trigger immense bursts of star formation, funnel gas to the center to feed growing supermassive black holes, and completely reshape a galaxy's structure, turning disordered, clumpy systems into the bulges and disks we recognize today. But when astronomers try to actually count these mergers by looking back in time, they run into a thorny problem. Different techniques yield different results. One common method is to simply look for visibly distorted galaxies. Using powerful telescopes like Hubble and now JWST, researchers scan deep fields for telltale signs of interaction. Tidal tails stretching out into space, warped disks, double nuclei, or pairs of galaxies so close they are clearly gravitationally entwined. This approach suggests a very active merger history, with the rate of interactions increasing steadily as we look back to higher redshifts. The early universe, by this visual evidence, was a tumultuous place. However, another technique tells a slightly different story. Instead of looking at shapes, this method uses a galaxy's stellar population as a forensic tool. When two galaxies merge, the event triggers a powerful starburst, forming a large number of new stars all at once. By carefully analyzing the ages of the stars within a modern galaxy, astronomers can reconstruct its history and identify past bursts of star formation that likely signal a major merger. This archaeological approach, applied to galaxies in our local universe, sometimes suggests a more gradual buildup, with mergers playing a significant but perhaps less dominant role than the visual counts imply. So why the discrepancy? The answer likely lies in the limitations of each method. Visual identification is incredibly difficult at the farthest distances. The faint, distant galaxies captured by our telescopes are often just tiny, fuzzy blobs. Subtle signs of interaction, like faint tidal tails, can be lost in the noise or fall below the resolution limit of the telescope. We might be missing a large number of mergers, especially minor ones. On the other hand, the stellar archaeology method has its own blind spots. Starbursts can be triggered by other events, like the inflow of gas along a cosmic filament, not just a merger. Furthermore, multiple smaller mergers can blur together in the historical record, making it hard to distinguish them from a few major events. The most exciting developments are coming from spectroscopic surveys. When two galaxies are about to merge, their different velocities can be detected by looking at the Doppler shift of their light. This allows astronomers to not just see a close pair, but to confirm they are gravitationally bound and on a collision course. New instruments are making this kind of analysis possible at greater distances, providing a more robust census of impending collisions in the early universe. The data so far points toward a complex reality where merger rates were indeed higher in the past, but perhaps not as dramatically as some visual studies suggested. The early cosmos was active and dynamic, with mergers serving as a crucial catalyst for change, but they were part of a symphony of growth processes that included more peaceful gas accretion, working in concert to build the galaxies we see today. But to truly understand the nature of the first starlight, we must ask a more fundamental question about the builders themselves. This leads us to our 16th mystery, a debate that cuts to the very core of how the cosmos got its start. What was the size range of those first stars? In our modern universe, when a giant cloud of gas collapses to form stars, it doesn't produce just one type. It creates a whole spectrum, from diminutive red dwarfs barely 1/10 the mass of our Sun to brilliant blue giants dozens of times heavier. This distribution is what astronomers call the initial mass function, and it's a crucial rulebook that dictates how a galaxy evolves, how brightly it shines, and what elements it forges. For a long time, the prevailing theory was that the first stars, population 3, played by a completely different set of rules. The logic was compelling. Without heavier elements like carbon and oxygen to help the gas cool and fragment efficiently, the collapsing clouds of pure hydrogen and helium would have been monolithic, forming only truly colossal stars, perhaps between 100 and 1,000 solar masses. This top-heavy initial mass function would mean the first stellar generation was a population of giants. This idea of an exclusive club of behemoths has profound implications. If every first star was massive, they would have all lived fast and died young in spectacular supernova. This would have seeded the early universe with heavy elements very quickly and uniformly. The light output from these first galaxies would have been staggering, dominated by the intense blue-white ultraviolet glare of massive stars, potentially explaining how reionization happened so rapidly. However, this neat picture has begun to crack under the weight of new theoretical models and observations. More sophisticated computer simulations that account for the complex physics of accretion disks and protostellar feedback are now suggesting that fragmentation might have been possible even in pristine gas. While the first stars likely leaned toward high masses, the emerging view is that the population may have been more diverse than we once thought. It's possible that alongside the true giants, there were also stars of lower mass, perhaps even some that were similar in size to our own Sun. The existence of even a small number of these low-mass first stars would change everything. A star with a mass less than that of our Sun has a lifespan longer than the current age of the universe. This means that if any low-mass population 3 stars formed, they should still be shining today, quietly burning in the halos of galaxies like our own. The hunt for these living fossils is one of astronomy's greatest quests. Finding just one would be like discovering a living dinosaur, a direct window into the cosmic dawn. Astronomers are tirelessly surveying the skies, looking for the most extremely metal-poor stars. The Holy Grail would be a star with absolutely no detectable heavy elements, a pure, uncontaminated relic from before the first supernova. So far, while we've found stars with incredibly low metal content, none have been completely metal-free. This could mean that low-mass population 3 stars are incredibly rare, that they never formed at all, or that we simply haven't found them yet. The debate over the first star's initial mass function isn't just academic. It directly affects how we interpret the light we see from the most distant galaxies with the James Webb Space Telescope. If the first stellar populations were top-heavy, dominated by massive stars, then early galaxies would have been extremely bright and blue for their mass. If the mass function was more normal, including many smaller, dimmer, redder stars, then the galaxies we are seeing must be even more massive than we currently estimate to account for their brightness. The answer also dictates the pace of early chemical enrichment. A top-heavy function would produce a sudden, widespread pollution of metals. A more varied function would lead to a more gradual and patchy enrichment process. Unraveling this mystery is key to calibrating our entire cosmic history, forcing us to ask whether the first chapter of star formation was a story exclusively about brilliant, short-lived giants, or if it also included a population of faint, enduring red dwarfs that are still shining in the darkness, waiting to be found. Yet for all the violent chaos of galactic mergers and the brilliant flashes of the first starlight, these events did not occur randomly in the void. They were guided by an immense, invisible architecture that began forming in the universe's infancy, a vast, interconnected network known as the cosmic web. This is the grand stage upon which the drama of cosmic dawn played out, and its rapid emergence presents one of the most profound mysteries in our study of the early universe. If you could pull back and view the cosmos on the largest scales, you wouldn't see a random scattering of galaxies. Instead, you'd witness an intricate, web-like structure of dazzling complexity. Galaxies are not scattered randomly. They are concentrated into enormous clusters, strung along vast filaments that stretch for hundreds of millions of light-years, all intersecting at dense nodes. Between these structures lie equally immense voids, enormous regions of near-total emptiness that can span hundreds of millions of light-years across. This is the cosmic web, the large-scale structure of the universe, and the puzzle is how this magnificent architecture was assembled with such breathtaking speed. The blueprint for this web was imprinted in the universe's earliest moments. The story begins with the Big Bang itself. In that first fleeting instant, quantum fluctuations, tiny, random variations in energy density, were happening on a subatomic scale. The rapid inflationary expansion of the universe that followed didn't just make the cosmos larger. It stretched these microscopic quantum wrinkles to astronomical proportions, freezing them into the fabric of spacetime. These infinitesimal density variations became the seeds for all future structure. We see their faint echo in the cosmic microwave background, a snapshot of the universe at 380,000 years old, which shows temperature variations of just 1 part in 100,000. These tiny ripples were the only unevenness in an otherwise smooth, expanding universe. Gravity is the engine that turned those subtle blueprints into a cosmic city. Over the eons that followed, gravity began to work its slow, relentless magic. Regions that were slightly denser than average had a bit more gravitational pull. They began to attract matter from their surroundings, growing ever so slightly denser, which in turn increased their gravitational pull, creating a powerful feedback loop. This is the process of gravitational instability, and it operated with an invisible partner, dark matter. This mysterious substance, which does not interact with light but has mass and feels gravity, is the true skeleton of the cosmic web. Because dark matter doesn't experience pressure or radiation, it could begin collapsing into structures long before the ordinary atomic gas could. It formed an invisible scaffolding of filaments and halos, and the ordinary matter, the hydrogen and helium gas, simply flowed along this pre-existing dark matter framework, settling into the wells and eventually forming the galaxies and stars that we can see. The deep mystery, however, lies in the timeline. Our most sophisticated supercomputer simulations, which meticulously follow the laws of physics and the influence of dark matter, consistently show this process as a stately, gradual affair. They predict that the cosmic web should have taken billions of years to mature into the intricate network we observe today, but our telescopes are now telling a different story. Observations from the James Webb Space Telescope and other instruments are revealing that the universe was far more structured, far earlier than these models predict. We are seeing fully formed galaxy clusters and well-defined filaments at redshifts that correspond to a time when the universe was less than 1 billion years old. It's as if we have a detailed model for how a great city like London should grow, predicting it would take 1,000 years to develop its complex infrastructure, but then we find archaeological evidence of a sprawling, modern-looking London just a century after the first settlement was built. The universe's construction crew appears to have worked at an astonishingly accelerated pace. This tension between simulation and observation forces us to question our understanding of the fundamental ingredients of the cosmos. Perhaps the properties of dark matter are not exactly as we've assumed in our models. The standard cold dark matter model posits particles that move slowly and clump easily on small scales. But if dark matter were slightly warm, with particles moving faster, it might suppress the formation of the very smallest structures, potentially altering the entire timeline of how the web assembles. Another possibility is that we are underestimating the role of ordinary matter, or baryons, in this early assembly. In our simulations, the gas often plays a passive role, simply flowing into the dark matter wells. But in reality, the gas has physics of its own. It can cool, it can be heated by the first stars and quasars, and it can generate powerful outflows that push back against gravity and even alter the distribution of dark matter itself. This baryonic feedback might have played a much more active role in shaping the early web than we've accounted for, potentially accelerating its development. There's also the tantalizing, though more speculative, idea that gravity itself might behave differently on the largest scales, or that another unknown force was at play in the early universe. Reconciling the observed rapid growth of the cosmic web with our theoretical predictions is one of the most active frontiers in cosmology. The answer will not only tell us how the universe built its grandest structures, but will also provide crucial clues about the nature of dark matter, the behavior of gravity, and the complex interplay between the luminous universe we see and the dark, invisible framework that holds it all together. Each new deep field image is like adding another piece to this cosmic map, bringing us closer to understanding how a nearly smooth primordial soup could so quickly transform into the most complex and beautiful architecture in all of existence. Scattered throughout the halos of galaxies like our Milky Way, we find some of the most ancient and densely packed stellar cities in the universe, globular clusters. These are magnificent spherical swarms of hundreds of thousands of stars, all gravitationally bound together in a volume so tight that the night sky from a planet within one would be a perpetual, dazzling twilight. They are universal phenomena appearing in all large galaxies, and their stars are among the oldest we have ever found, with ages dating back to within 1 billion years of the Big Bang. This makes them living relics from the epoch of the first galaxies, but their precise origin story presents us with a classic cosmic chicken or egg dilemma. Did these clusters form before, during, or after the galaxies they now call home? The stars within a globular cluster tell a very clear story of rapid, intense birth. Their chemical composition is remarkably uniform but also extremely metal poor, indicating they all formed together in a single, furious burst of star formation from a pristine or lightly enriched cloud of gas very early in cosmic history. They represent a mode of star formation that was incredibly efficient, turning a vast amount of gas into stars in a very short period with almost no waste. This is completely different from the more sedate, ongoing star formation we see in galactic disks today. To achieve this, the conditions must have been exceptional. A cloud of gas that was incredibly dense and under tremendous pressure, allowing it to collapse en masse without fragmenting into many smaller stellar nurseries over a long period. The question is, what could possibly create such perfect, intense conditions in the chaotic early universe? One compelling theory places their birth squarely within the tumultuous environment of the first proto-galaxies. In this scenario, the early, gas-rich galaxies were not smooth disks but the chaotic, clumpy systems we discussed earlier. The most massive and dense of these collapsing gas clumps could have been the perfect nurseries for globular clusters. As these clumps swirled within the young galaxy, their immense density would have allowed them to resist being torn apart by tidal forces long enough to undergo a single, coordinated collapse, forming a bound cluster of stars. The cluster would then survive as the galaxy itself evolved around it, eventually being pushed out into the galactic halo as a consequence of mergers and dynamical interactions over billions of years. In this view, the clusters are like enduring pieces of the original construction material, the densest knots that held together as the galaxy was assembled around them. A second, more radical hypothesis suggests that globular clusters could be the very first structures to have formed before any recognizable galaxy even existed. This idea hinges on the unique properties of the early cosmic web. At the intersections of the first dark matter filaments, the density of matter would have been exceptionally high. Perhaps within these specific, extreme environments, pockets of gas were able to collapse directly under their own gravity, igniting a tremendous burst of star formation that created a bound cluster. This primordial cluster would then act as a gravitational seed, its mass helping to attract more dark matter and gas, eventually becoming the nucleus around which an entire galaxy assembled. In this case, the galaxy formed around the cluster, not the other way around. This would make globular clusters the true pioneers, the first stable structures to emerge from the darkness, with galaxies growing like cities around these ancient town centers. A third possibility involves the incredible violence of galaxy collisions. The early universe was a crowded and chaotic place, and when two young, gas-rich galaxies merged, the collision would have sent immense shockwaves through their interstellar gas. These shocks could have compressed vast clouds of gas to the extraordinary densities required to trigger the formation of a globular cluster in a single, rapid event. This theory could explain why we sometimes see bursts of new globular cluster formation associated with galaxy mergers in the more recent universe. If this was a primary method, then many of the oldest clusters might not be the absolute first structures, but rather the products of the first major waves of galactic assembly and destruction. The challenge in choosing between these theories is that globular clusters are notoriously difficult to date with absolute precision. While we know their stars are ancient, pinning down whether they formed just a few 100 million years after the Big Bang or a full billion years later is incredibly difficult. Furthermore, their survival for over 13 billion years is a feat in itself. A cluster must be incredibly dense to avoid being torn apart by the tidal gravitational forces of its host galaxy. Many clusters would have been destroyed over the eons, meaning the ones we see today are only the survivors, the densest and most resilient of their kind. This survivor bias makes it hard to reconstruct the complete population that once existed. Unraveling this mystery is more than an academic exercise. It's key to understanding the conditions within the first galaxies. The ability to form a globular cluster tells us about the pressure, temperature, and density of the gas in that specific place and time. By studying the chemical patterns in the stars of different clusters, we can trace the enrichment history of the early universe. Were they all forged from pristine gas, or do some show the signature of enrichment from a single previous supernova? The James Webb Space Telescope is now turning its infrared gaze toward these ancient stellar systems, not to see them as the fuzzy balls of light we observe from nearby, but to resolve their individual stars in galaxies millions of light years away. By comparing clusters in different galactic environments and at different distances, and thus different look-back times, we hope to finally chart their birth and determine whether they are the foundational seeds of galaxies or their first and most enduring masterpieces. Yet as we map the grand architecture of the early cosmic web and its ancient stellar survivors, we encounter a class of objects that seems to defy the very logic of galaxy growth itself. Imagine a galaxy that packs the same stellar mass as our own Milky Way, a system of hundreds of billions of stars, but instead of being spread across a vast disk 100,000 light-years wide, it is squeezed into a region less than 1/20th the size, a tiny, brilliant nugget of starlight. According to our traditional understanding of galaxy formation, such an object shouldn't exist. It would be like finding a fully grown ancient redwood tree somehow contained within the space of a single acorn. Yet this is precisely what our telescopes have revealed. Scattered throughout the early universe are these compact, massive galaxies, and their existence presents a profound puzzle about the physical conditions of the cosmos during its formative years. The discovery of these dense galaxies was a genuine shock to astronomers. When the Hubble Space Telescope began its deep field observations, it found these small, reddish, seemingly insignificant smudges at high redshifts. Initially, they were assumed to be minor players in the cosmic story, but when astronomers later used other instruments to measure their masses, primarily by observing how fast stars were moving within them, the results were staggering. The high velocities indicated a tremendous amount of mass was crammed into that tiny volume, governed by the relentless pull of gravity. These weren't minor clumps, they were stellar cities of immense density, boasting masses tens to hundreds of billions of times that of our Sun within a diameter of only a few thousand light-years. Our own Milky Way, by comparison, achieves a similar mass but is vastly more spread out and diffuse. The key question is how the early universe could possibly manufacture such dense, massive objects so quickly, and why we hardly ever see their counterparts in the nearby universe today. The explanation for their formation likely lies in the unique environment of the early cosmos. Remember, the universe was a much denser place only a billion years after the Big Bang. The matter that would eventually form a galaxy was concentrated into a far smaller volume of space due to the overall smaller scale of the universe. Furthermore, the primary mode of growth for these early systems was through the rapid, relentless accretion of cold gas streaming in along the filaments of the cosmic web. This gas could fall directly into the center of the growing galaxy with tremendous efficiency, fueling an incredibly intense, centrally concentrated burst of star formation. There was little time for the galaxy to settle into a calm, rotating disk. Instead, it formed stars in a furious, monolithic collapse, piling up its mass in a very small region. The process might have been so efficient and rapid that it created these ultra-dense stellar cores before other processes could spread them out. But if they formed so readily in the early universe, where did they all go? Their scarcity in the modern cosmos is the second half of this mystery. We simply do not find many galaxies of such extreme density nearby. The leading theory for their disappearance is not that they vanished, but that they transformed. Astronomers believe these compact nuggets are actually the progenitors of the giant elliptical galaxies we see at the hearts of today's massive galaxy clusters. The mechanism for this transformation is thought to be a specific, violent type of galactic merger known as dry merging. Over billions of years, these dense galaxies did not grow by accreting more gas to form new stars. Instead, they underwent a series of mergers with other, smaller galaxies that had already used up their own gas and stopped forming stars, hence the term dry. Unlike a wet merger full of gas that triggers new star formation, a dry merger is mostly a gravitational event. When two such gas-poor systems merge, their stars are stirred up and redistributed, puffing up the galaxy's size without adding much new mass. A series of these minor mergers over cosmic time could slowly and steadily inflate the once compact galaxy into the much larger, more diffuse elliptical galaxy we observe today. The dense core of that ancient galaxy would still remain at the center, and indeed many massive ellipticals do contain a compact, ancient nucleus of stars that matches this description perfectly. This evolutionary path suggests that the most majestic galaxies in our present universe may have begun their lives as these incredibly dense, brilliant seeds, whose true nature is only now being revealed as we look back to the dawn of time. But even as we map the grand structures of the cosmos, from the brilliant quasars to the faintest dwarf galaxies, we stumble upon a mystery that is both fundamental and humbling, a simple case of missing matter. Not the elusive dark matter, but the ordinary atomic stuff we're made of protons, neutrons, and electrons. This is the mystery of the missing baryons. The Big Bang Theory makes an incredibly precise prediction. By studying the relative abundances of the light elements forged in the first few minutes, hydrogen, helium, lithium, we can calculate exactly how much of this normal or baryonic matter the universe should contain. The math is clear and well established, yet when astronomers add up all the normal matter, they can actually see in the early universe all the stars, all the gas within galaxies, all the dust, they come up drastically short. By some estimates, we can only account for about half of the baryonic matter that our models insist must be there. It's a cosmic accounting error of epic proportions, and it forces us to ask a deceptively simple question: where did the rest of it go? This isn't a case of matter being destroyed, it's a case of it being incredibly well hidden. The leading hypothesis is that this missing matter isn't gathered in neat, glowing packages like stars and galaxies. Instead, it's spread out in an immense, diffuse web of incredibly hot and incredibly thin gas that fills the vast spaces between galaxies. Astronomers call this the warm-hot intergalactic medium, or WIM for short. Picture this not as a fog, but as a super-tenuous plasma, a soup of ionized gas heated to temperatures between 100,000 and 10 million degrees. At these temperatures, the gas is so energetic that it doesn't emit light in the way cool, dense gas does. It's essentially invisible to most of our telescopes. Its primary signature would be a subtle absorption of very specific high-energy light, like that from distant quasars as the photons pass through these vast hot reservoirs. Finding this faint fingerprint is like trying to spot a single, specific heated wire in a spider's web by shining a flashlight through it from a mile away. The evidence for the WIM has been tentative, a series of tantalizing hints in the spectra of distant objects, but a conclusive census has remained frustratingly out of reach. Another prime hiding place is closer to home, or rather, closer to galaxies. This is the circumgalactic medium, a vast and dynamic halo of gas that surrounds every galaxy. Think of it as a galaxy's extended atmosphere, a reservoir of material that is both falling in to fuel future star formation and being blown out by the powerful winds from supernova and active black holes. This gas can exist in a multitude of states: cold clouds, warm filaments, and hot plasma, all swirling around in a complex ecosystem. Because it is so diffuse and often not in a state to emit light easily, a significant portion of a galaxy's baryonic mass could be lurking in this extended halo, effectively invisible to our conventional observations. The combined mass of these circumgalactic halos across all galaxies could represent a huge fraction of the missing matter, a vital component of the cosmic budget that we are only just beginning to appreciate and measure with new, sensitive instruments. Solving this mystery is critical because it completes the universe's ledger. Until we can account for every atom predicted by the Big Bang, our understanding of cosmic evolution is incomplete. The journey of baryonic matter from its creation in the primordial fireball to its distribution into stars, galaxies, and these hidden reservoirs is the central narrative of structure formation. Finding the missing baryons would close this chapter, confirming that our model of the universe is not only correct on the largest scales, but also in its most fundamental inventory. New observatories like X-ray telescopes designed to detect the faint emission from million-degree gas and ultraviolet spectrographs that can find the absorption signatures of warmer filaments are now on the hunt. They are peering into the voids between the galaxies, searching for the ghostly glow of the WIM and mapping the intricate structure of the circumgalactic medium, slowly solving this cosmic missing persons case for the atoms that make up everything we see and are. Yet as we chart the visible components of the early universe, from stars to galaxies to gas, we must now turn our attention to an invisible force that subtly but profoundly shaped everything: magnetism. This brings us to a mystery that probes the very fabric of spacetime itself, the origin of the first cosmic magnetic fields. We are all familiar with magnetism on a small scale, from the simple pull of a refrigerator magnet to the vast field that surrounds our entire planet. But magnetism is not just a local phenomenon, it is woven throughout the cosmos. We detect magnetic fields threading through the interstellar space of our galaxy, influencing the motion of gas, the formation of stars, and even the propagation of cosmic rays. The question is, where did these universe-spanning fields come from? Were they present at the very beginning, imprinted during the Big Bang itself, or were they forged later in the cosmic furnace of the first stars and galaxies? The concept of a primordial magnetic field is a captivating one. This theory suggests that the seeds of magnetism were planted in the universe's infancy, during a period of rapid inflation or a phase transition in the primordial plasma. In this view, tiny magnetic fields were generated by quantum fluctuations and then stretched to astronomical scales by the universe's exponential expansion, creating a weak but pervasive background field that would have filled all of space. If such a field existed, its faint imprint might still be detectable today, perhaps as a subtle pattern in the polarization of the cosmic microwave background. Finding this signature would be a monumental discovery, providing a direct window into physics at energy scales far beyond anything we can achieve in particle accelerators. However, despite extensive searches, no conclusive evidence for such a primordial field has been found, leaving this elegant idea in the realm of compelling speculation. The alternative, and perhaps more widely accepted, theory is that magnetic fields were born from chaos emerging from the turbulent, dynamic environments of the early universe through astrophysical processes. In this scenario, the first magnetic fields were incredibly weak, perhaps generated by the Biermann battery effect, a process that can create magnetism in a plasma where there are differences in temperature and pressure. Imagine the first supernova explosions or the powerful shock waves from galaxy collisions. In these tremendously violent events, electrons and ions can be separated and sent flowing at different rates, generating tiny electrical currents and consequently minuscule magnetic fields. These initial fields would have been astonishingly feeble, billions of times weaker than Earth's magnetic field. The real mystery is not their birth, but their incredible amplification. How did these weak seeds grow to become the powerful forces that shape galaxies today? The answer lies in a powerful cosmic dynamo. Once a weak seed field exists, it can be amplified and sustained by the motion of conducting plasmas like the ionized gas that fills space. This is similar to how a simple bicycle dynamo works. Rotational motion is converted into electrical current and magnetic energy. In the cosmic context, this requires turbulence and rotation on a colossal scale. As gas collapsed to form the first galaxies and stars, it would have spun up, creating massive disks and vortices. The turbulent motions within these spinning structures could have stretched, twisted, and folded the weak magnetic field lines, transferring energy from the mechanical motion of the gas into the magnetic field, amplifying it exponentially over time. A protogalactic disk swirling with immense currents of plasma would have acted as a perfect engine for this magnetic amplification, potentially strengthening a field by a factor of 1 trillion in just a few 100 million years. The influence of these growing magnetic fields cannot be overstated. While gravity is the primary architect of cosmic structure, magnetism acts as a crucial regulator. Within a collapsing cloud of gas, magnetic fields provide pressure and support, resisting gravity's pull and helping to control the rate at which stars form. They can channel ionized gas, directing flows along field lines and influencing the formation of jets and outflows from young stars and active black holes. On a galactic scale, magnetic fields help shape the entire ecosystem of a galaxy. They contribute to the stability of spiral arms, confine cosmic rays, and likely play a vital role in launching the colossal galactic winds that vent material out into intergalactic space, a process critical for regulating galaxy growth and distributing those missing baryons. The emergence of magnetism was not merely a side effect of cosmic evolution. It was a fundamental transition that added a new force to the physics of the cosmos, one that brought a new level of order and complexity to the once featureless expanse and continues to influence the life cycle of every galaxy we see. This brings us to a subtle but deeply puzzling force that governed the growth of the earliest galaxies, a concept known as galaxy assembly bias. For a long time, the prevailing wisdom in cosmology was beautifully simple. A galaxy's destiny is written primarily by its mass. The total amount of dark matter in its halo was thought to be the master controller, dictating how much gas it could pull in, how many stars it could form, and what its final structure would look like. Two halos of the same mass, according to this view, should host galaxies that are essentially twins regardless of where they formed or when. But the universe, it turns out, is far more nuanced. Astronomers began to notice that galaxies with identical halo masses could have strikingly different properties. One might be a vibrant, star-forming spiral, while another could be a quiescent, red and dead elliptical. This discrepancy suggests that a galaxy's fate is not determined by mass alone, but is also profoundly influenced by its entire history and its address within the cosmic web, a mysterious connection that our standard models struggle to explain. This phenomenon, assembly bias, reveals that the timing of a galaxy's formation and its specific location in the large-scale structure of the universe impart a kind of cosmic ancestry, a hidden variable that shapes its evolution. Imagine two dark matter halos that have exactly the same mass today. One formed early in a dense region at the intersection of two massive filaments in the cosmic web. The other assembled more recently in a quieter, more isolated suburban void. Even though their scales read the same, their life stories are completely different. The early forming halo in the dense urban environment experienced a rapid, violent youth. It was bombarded by mergers and surrounded by neighboring galaxies, its gas heated by the intense radiation field of the early universe. This galaxy likely exhausted its fuel quickly, its star formation quenched by these harsh conditions, leaving it a red, aging elliptical. The halo in the void, however, had a more peaceful existence. It grew gradually through the steady accretion of cold gas, allowing for sustained star formation and the development of a neat, rotating disk. Mass alone cannot account for these divergent paths. The environment itself imprints a bias on how galaxies assemble. Unraveling this mystery forces us to consider the complex interplay between a galaxy and its surroundings. A halo's location within the cosmic web doesn't just determine how many neighbors it has, it dictates the very mode of growth. Halos in dense clusters are primarily shaped by major mergers, dramatic events that can destroy disks, trigger immense starbursts, and feed central black holes. Halos in the quiet filaments, however, grow through a more gentle process called smooth accretion, where cold gas streams flow directly onto the galaxy, fueling steady and prolonged star formation. This environmental influence creates a fascinating cosmic diversity that our models, which often treat dark matter halos as isolated islands, are only beginning to incorporate. The challenge is that these large-scale environmental effects operate on scales far larger than the galaxies themselves, requiring enormous, computationally expensive simulations to even begin to model properly. The implications of assembly bias extend far beyond academic curiosity. It is a crucial piece in solving other cosmic puzzles. For instance, it might help explain why some small dwarf galaxies are completely devoid of gas and stars while others of similar mass are still actively forming them. A dwarf galaxy that fell into a massive cluster early in its history would have had its gas stripped away by the hot intracluster medium, a process known as ram pressure stripping. A dwarf of the same mass that remained isolated in a void could hold onto its gas indefinitely. This bias in their assembly history, dictated by their environment, creates the variety we observe. As our telescopes peer further back in time, they are beginning to map this environmental dependence in the early universe, searching for the first signs of how a galaxy's address within the infant cosmic web predetermined its destiny, adding a rich and complex layer to the story of how our universe evolved from simplicity to the magnificent diversity we see today. Yet for all their brilliance, the first stars and galaxies were fundamentally transparent, made of nothing but the pristine hydrogen and helium forged in the Big Bang. But our modern universe is filled with something else, something dark and gritty that plays a silent, crucial role in the cosmic cycle of life and death: dust. This brings us to a surprisingly gritty mystery: the origin of the very first dust grains. These are not the dust bunnies under your bed. These are microscopic particles of carbon, silicon, and other heavy elements, and their formation marked a quiet revolution in how the universe built its structures. Without dust, the cosmos as we know it might not exist. To understand why, we need to look at a star-forming cloud in a modern galaxy. While the first stars relied on the fragile cooling of molecular hydrogen, today's gas clouds have a far more efficient way to shed heat. They use dust. These tiny solid particles are incredibly effective at radiating thermal energy away in the form of infrared light. As a cloud collapses, the dust inside it cools it down, allowing the gas to fragment into much smaller, denser clumps. This is why star formation in the modern universe can produce a whole spectrum of stars, from massive giants to small red dwarfs. The presence of dust essentially allows a gas cloud to break apart into 100 pieces instead of just one monolithic clump. It makes the entire process of star formation more efficient and far more democratic. So the emergence of the first dust grains was a pivotal moment, a transition from an era of isolated stellar titans to one where galaxies could become bustling factories producing stars of all sizes. The question is, in a universe initially devoid of any heavy elements, where did the very first specks of this cosmic grit come from? The prime suspects are the dramatic deaths of the first stars. A supernova explosion is a titanic event, unleashing energies that can forge every element in the periodic table. In the expanding, cooling ejecta of these explosions, atoms can bump into each other and stick together, forming tiny seed clusters that eventually grow into full-fledged dust grains. Theoretical models suggest that a single supernova could produce an astonishing amount of dust, anywhere from 1/10 of a solar mass to even a full solar mass or more of solid material. This dust would then be blasted out into the surrounding space by the supernova shockwave, polluting the interstellar medium with the first solid matter. For a long time, supernovae were considered the obvious and primary source of this first dust. However, there's another, slower and more methodical contender: the asymptotic giant branch stars, or AGB stars. These are not massive stars that die young, but intermediate mass stars, several times the mass of our Sun, in the final, unstable stages of their long lives. In their extended, cool atmospheres, conditions are perfect for a gradual soot-like process. Atoms of carbon and other elements can condense out, layer by layer, forming vast quantities of dust that are then gently pushed out into space by the star's radiation pressure, creating a beautiful, dusty planetary nebula. The dust from AGB stars is often different in composition from supernova dust, tending to be richer in carbon. The problem with AGB stars as the first dust producers is one of timing. These stars take hundreds of millions, even billions, of years to reach this late stage of their evolution. If dust didn't appear until the first AGB stars died, the early universe should have remained a place of only massive star formation for a very long time. But our observations are telling a different and mysterious story. When astronomers use powerful telescopes like ALMA and the James Webb Space Telescope to look back at galaxies existing just 700 or 800 million years after the Big Bang, they find something astounding. These young galaxies are already dusty. We can detect the telltale signature of dust by seeing how it reddens and obscures the light from stars, or more directly, by detecting its emission in the far infrared part of the spectrum. This is far too early for the first AGB stars to have contributed in any significant way. Their slow evolution means they wouldn't have started producing dust until the universe was at least 1 billion, probably 2 billion years old. The early presence of dust forces us to conclude that supernova must have been the dominant dust factories in the universe's first billion years. They are the only stellar engines powerful and fast enough to have enriched the cosmos so quickly. Yet, this conclusion comes with its own set of puzzles. Surviving the intense environment of a supernova is a tough journey for a fragile dust grain. The very same shockwave that propels the dust out into space can also destroy it. As the dust plows into the surrounding interstellar gas, high-energy collisions and sputtering processes can blast the grains apart, turning them back into individual atoms. How much of the dust produced in a supernova actually survives to enrich the galaxy? Estimates vary wildly, and it's possible that the efficiency of dust production and survival in these early explosions was much higher than we see in supernova today, perhaps due to different gas densities or explosion energies. The hunt is now on to find direct evidence of this first dust. By studying the most metal-poor stars in our galaxy, we can look for chemical signatures in their atmospheres that might have been imprinted by dust from a single, first-generation supernova. Each tiny grain of dust, a silent speck from a long-dead star, carries within it the story of the universe's transition from a simple, elemental soup to a complex, gritty environment capable of building planets and ultimately us. Yet as we piece together the history of the first stars and galaxies by studying the individual points of light we can resolve, we encounter a profound puzzle that comes not from what we see, but from the faint, collective glow we can't quite explain. This is the mystery of the cosmic infrared background. Imagine turning off all the stars and galaxies in the sky. Instead of perfect blackness, you'd be left with a faint, pervasive, and uniform glow of infrared light that fills the entire universe. This isn't the famed cosmic microwave background from the Big Bang. This is something else entirely. It's the combined heat signature of every star and galaxy that has ever existed, their light stretched by the expansion of the universe into the infrared part of the spectrum. But when astronomers carefully measure the total amount of energy in this diffuse background, and then add up the light from every galaxy we've ever observed, the numbers don't match. There's a significant excess, an unexplained infrared glow that suggests the universe was far busier in its youth than our census of galaxies can account for. It's as if we tried to measure the total sound in a vast, crowded room by listening to every individual conversation we could pick out, only to discover that the overall noise level is much louder, hinting at a hidden crowd of murmuring voices we simply can't see. This missing light presents a fascinating cosmic detective story. The most straightforward explanation is that our inventories of the early universe are simply incomplete. Our most powerful telescopes like Hubble and even the James Webb Space Telescope have their limits. They can only see the brightest, most massive galaxies at the farthest distances. But what if the early universe was also filled with an immense population of incredibly faint, low-mass dwarf galaxies, or galaxies that are heavily obscured by vast shrouds of dust? These dim systems could be churning out stars at a prodigious rate, but their individual light is too faint to be detected by our current instruments. Their collective output, however, would add up, contributing to that mysterious background glow. This would mean our current picture of cosmic dawn is like viewing a grand city from miles away at night. We can easily pick out the bright downtown skyscrapers and major highways, but we're completely missing the light from countless dim suburban streets and homes, even though their combined contribution is significant. If this is the case, then the early universe was even more efficient at building structures than we thought, and future, more sensitive telescopes should eventually be able to resolve these faint galaxies, turning this background glow into a multitude of individual points of light. However, there are more exotic possibilities on the table. Perhaps the excess isn't from galaxies at all, but from something entirely different. One compelling, though highly speculative, idea involves the very first stars. If the earliest population of stars included a significant number of enormous, metal-free behemoths, they would have been incredibly efficient at producing ultraviolet light. This light would then have been redshifted into the infrared by the expansion of the universe. The combined output of these primordial giants, even if they lived very short lives, could potentially contribute a large fraction of the background. Another, even more radical theory points to the process of cosmic structure formation itself. As the first massive black holes and galaxies began to form, vast amounts of gas would have been funneled into deep gravitational wells. The incredible release of gravitational energy as this gas fell in could have heated it to the point where it glowed brightly in the infrared, adding to the diffuse background in a way that isn't tied to starlight at all. This would mean the background is not just a fossil record of starlight, but also a fossil record of the cosmic web itself, illuminated by the sheer violence of gas crashing into the first dark matter halos. The challenge in solving this mystery lies in the extreme difficulty of the measurement. Isolating the cosmic infrared background is like trying to measure the faint glow of a distant city while standing in the middle of a brightly lit football stadium. Astronomers must first meticulously subtract all the foreground light from our own solar system's dust cloud, then the light from stars and galaxies within our own Milky Way, and finally the aggregated light from all the resolved galaxies in the distant universe. What's left should, in theory, be zero. The fact that it isn't zero is what makes this such a tantalizing anomaly. Different missions from Spitzer to Herschel to Akari have all measured this excess, confirming it is a real phenomenon and not an instrumental error. The James Webb Space Telescope is now joining this hunt, not by studying the background itself, but by pushing to the absolute limits of its sensitivity to see if it can finally resolve those legions of faint, early galaxies. If it can, and their total light accounts for the excess, the mystery will be solved. But if the background glow remains even after Webb has counted every conceivable faint smudge of light, then we are forced to consider that something truly fundamental is missing from our story of the universe's first few billion years, a hidden chapter written in the faint, warm light that fills the spaces between everything. The serene image of early galaxies as peaceful stellar nurseries couldn't be further from the truth. In reality, they were more like cosmic pressure cookers, constantly venting colossal fountains of their own material out into the void. This brings us to a powerful and dynamic process that fundamentally sculpted the growth of all galaxies, the first galactic winds. Imagine a young, vibrant galaxy furiously forming its first generation of massive stars. It should be a golden age of construction, but instead of simply growing larger, this galaxy is actively tearing itself apart. From its core, a hurricane of superheated gas is being ejected at speeds of thousands of kilometers per second, a tempest so powerful it can blow the galaxy's entire future fuel supply clear out into intergalactic space. This isn't a rare catastrophe, it's a standard part of a young galaxy's life cycle, a self-regulating mechanism that determined which galaxies would become giants and which would be stunted for eternity. The driving forces behind these immense outflows are as violent as the winds themselves, a trio of cosmic engines working in concert or alone. The most widespread driver is undoubtedly the collective fury of supernova. In a region of intense star formation, massive stars are living and dying in rapid succession. Each supernova explosion is a titanic detonation, and when they occur in close proximity, their individual shockwaves can merge into a single, gigantic superbubble. This bubble expands rapidly, bursting out of the galactic disk like a volcanic eruption, carrying with it a mixture of heavy elements and pristine hydrogen gas. It's a storm of the galaxy's own making, fueled by the very stars it just created. The second engine is radiation pressure, a more subtle but equally potent force. Those same massive stars pour out an unbelievable flood of ultraviolet photons. While these particles of light have no mass, they carry momentum. When they slam into dust grains within the galactic gas clouds, they can physically push that material outward like a cosmic sandblaster. In the pristine environments of the earliest galaxies, this process might have been especially effective at driving away gas before it could even collapse to form the next generation of stars. But the most powerful winds of all likely came from a third, more monstrous source, active galactic nuclei, or AN. When a supermassive black hole at the center of a galaxy goes on a feeding frenzy, it doesn't just quietly consume matter. As gas spirals down into the black hole's gravitational well, it forms a searingly hot accretion disk that blasts out intense radiation. Along the black hole's rotation axis, magnetic fields can funnel some of this infalling material into jets that shoot out at nearly the speed of light. Even without jets, the sheer radiative power from the quasar can heat the surrounding gas to millions of degrees, causing it to expand outward in a tremendous hot wind. These AGN-driven winds are thought to be the most energetic of all, capable of affecting an entire galaxy at once and shutting down star formation on a global scale. The question for astronomers is not which one of these processes occurred, but rather which one dominated the feedback cycle in the universe's first few billion years, and how they interacted to create the galaxies we see today. The impact of these winds was nothing short of transformative for the evolving cosmos. On a local scale, they acted as a crucial thermostat for star formation. By ejecting gas, they literally removed the fuel for future stars, preventing a galaxy from turning all of its mass into stars in one frantic burst. This self-regulation is why galaxies are so inefficient at converting gas into stars. Without these feedback processes, we might live in a universe where galaxies burn through their fuel in a few 100 million years, leaving behind a dark and sterile cosmos. The winds also enriched the intergalactic medium. They were the primary delivery system for the heavy elements forged in stellar cores and supernova, spraying carbon, oxygen, iron, and other essentials for planet formation out into the vast voids between galaxies. This pollution of the pristine cosmic environment was a vital step, as it allowed future generations of stars and planets to form from already enriched material. Furthermore, by heating the surrounding gas, these winds could prevent it from cooling and falling back into the galaxy, effectively cutting off future growth. For small, low-mass galaxies with shallow gravitational wells, a single strong burst of star formation and its subsequent winds could be a death sentence, blowing away their gas and leaving them as faint, dark matter-dominated fossils. For larger galaxies, the winds might only pause star formation for a time, or perhaps even compress gas in their outskirts, triggering a new wave of star formation in a different location. The legacy of these first great outflows is written in the very distribution of matter we see around us, a testament to the fact that the early universe was not a place of quiet growth, but of violent, beautiful, and necessary chaos. But just as we chart the vast outflows from early galaxies, we encounter a structural puzzle much closer to home, a mystery that revolves around our very own cosmic neighborhood. Look at the satellite galaxies orbiting the Milky Way, the dozens of smaller systems like the Large and Small Magellanic Clouds that are gravitationally bound to our much larger spiral galaxy. According to our standard model of cosmology, these satellites should be arranged in a roughly spherical swarm, orbiting in random directions. This is because the dark matter halo that envelops our galaxy is predicted to be spherical itself, and the satellites which are thought to be embedded within this halo should reflect that distribution. They are the surviving remnants of the first building blocks that merged to form the Milky Way, and their orbits should tell the story of that chaotic, random assembly process. The reality, however, presents a startling contradiction. Instead of a chaotic swarm, many of the Milky Way's satellites, along with those around our sister galaxy Andromeda, are arranged in a highly organized and perplexing manner. They seem to be orbiting along a single, vast, thin plane, a great polar structure that looks more like a cosmic ring or disk than a random cloud. It's as if you tossed a handful of marbles into the air expecting them to scatter randomly, only to watch them neatly arrange themselves into a single spinning circle. This is the satellite plane problem, and it represents a serious challenge to our understanding of how galaxies form within the lambda-cold dark matter model. If dark matter halos are smooth and spherical, how can the objects moving within them exhibit such a pronounced and seemingly coordinated preference for a single plane? This isn't a minor statistical fluke. The plane around the Milky Way is remarkably thin, and the satellites within it are not just aligned in position. Their orbits are also correlated, with many moving in the same direction along this vast disk. The discovery of a similar, perhaps even more pronounced, planar alignment around the Andromeda galaxy deepens the mystery, suggesting this might be a common feature of large spiral galaxies and not just a strange local anomaly. For the standard model, this is a significant headache. The model's incredible success lies in explaining the universe on the largest scales, the cosmic web, the distribution of galaxy clusters. But here, on the scale of a single galactic halo, it appears to make a prediction that is starkly at odds with what we observe in our own backyard. This discrepancy forces astronomers to consider some truly fascinating possibilities. One line of explanation tries to solve the problem within the existing dark matter paradigm. Perhaps these planar structures are not primordial but were formed more recently through tidal interactions. A particularly massive merger event in the past could have ripped a dwarf galaxy apart, stringing its debris along a tidal stream that later coalesced into multiple satellite galaxies, all sharing the same orbital plane. Alternatively, the plane could be a transient feature, a cosmic coincidence that will eventually dissolve over many billions of years as orbits are perturbed and randomized. The challenge for these ideas is that the planes appear dynamically stable and contain a significant fraction of each galaxy's satellite population, making a single, recent tidal event an unlikely sculptor for such a predominant structure. The persistence of this mystery has led some scientists to propose more radical solutions that lie outside the standard model. One compelling idea involves alternative theories of gravity, most notably modified Newtonian dynamics, or MN. This framework suggests that we don't need dark matter to explain galactic rotations. Instead, the laws of gravity as defined by Newton and Einstein require a slight modification at very low accelerations, which are common in the outskirts of galaxies. Intriguingly, some versions of MUN naturally predict that satellite galaxies should form a disk-like distribution around their host, much like the planets orbit the Sun in a plane due to the way the solar system formed from a spinning disk. In this view, the satellite planes are not a problem to be solved but an expected outcome, a powerful piece of evidence that could point toward a fundamental revision of our understanding of gravity itself. Yet the debate is far from settled. New data from surveys like the European Space Agency's Gaia mission is providing incredibly precise measurements of the positions and motions of these satellite galaxies, allowing us to trace their orbits backward in time with unprecedented accuracy. This is helping us determine whether these planes are long-lived, stable structures or fleeting alignments. Furthermore, the next generation of wide-field telescopes such as the Vera-C Rubin Observatory will discover hundreds more faint dwarf galaxies around the Milky Way and Andromeda. A comprehensive census will show us if the planar alignment holds true for the entire population or if it's just a feature of the brighter satellites we've found so far. The solution to the satellite plane problem will therefore have profound implications, either revealing a new and unexpected aspect of how dark matter halos are structured or forcing us to reconsider the fundamental laws of physics that have guided our picture of the cosmos for the past century. But just as we've mapped the grand outflows and satellite structures, we must zoom in from the galactic scale to the very cradles of starlight themselves. This brings us to a question that strikes at the heart of how the first luminous structures assembled. Did the first stars emerge as solitary pioneers, or were they born in colossal, dazzling clusters? The distinction is critical, as the mode of that first star formation would have set the entire evolutionary trajectory for everything that followed, from the chemical enrichment of the cosmos to the very building blocks of galaxies. For a long time, the prevailing image was one of isolated behemoths, with a single monstrous star forming at the heart of each dark matter minihalo. The logic was that without metals to cool the gas efficiently, the collapse of a primordial cloud would be monolithic, unable to fragment into multiple smaller entities. In this scenario, the first lights in the universe would have flickered on one by one, scattered far apart in the vast darkness, each a lonely titan blazing against the void. However, more recent and sophisticated supercomputer simulations are painting a far more social and dramatic picture. These virtual recreations of the early universe suggest that the first stars were indeed born in groups, not in isolation. The process likely began when a vast cloud of pristine hydrogen and helium, hundreds of light years across, began to collapse within the gravitational well of a dark matter halo. As this cloud contracted, it didn't simply funnel all its material into a single point. Instead, the complex interplay of gravity, turbulence, and the gas's own physics caused it to break apart, fragmenting into several dense, massive knots. Each of these knots continued to collapse independently, ultimately igniting fusion and becoming a star. The result wouldn't have been a single star, but a small, dense cluster of perhaps 10 to 100 massive stars, all born from the same parental cloud and gravitationally bound to one another. This cluster would have been a breathtaking sight, a tight-knit family of brilliant blue-white giants, each shining millions of times brighter than our Sun, lighting up the cosmic darkness not as a single candle, but as a brilliant chandelier. This shift from a solitary to a clustered origin has profound implications. A cluster is a far more efficient and violent engine for transforming the early universe than a collection of isolated stars. First, consider the stellar feedback. In a dense cluster, the combined ultraviolet radiation and stellar winds from dozens of massive stars would have created a powerful, collective H2 region, a vast bubble of ionized hydrogen gas around the entire cluster. This collective feedback is much more effective at heating the surrounding intergalactic medium and blowing away residual gas than the output of a single star could ever be. It would have quickly sterilized the local environment, shutting down further star formation for a considerable distance and potentially expelling the enriched material from the first supernova far out into the cosmic web. Secondly, the deaths of these stars would have been a concentrated spectacle. If multiple stars in a cluster went supernova in quick succession, their shockwaves could have combined into a super bubble of incredible power, violently scattering the first heavy elements and potentially triggering a second wave of star formation in the compressed shell of gas at the bubble's edge. This creates a far more dynamic and interconnected story of life, death, and rebirth. This clustered beginning might also explain one of the most enduring mysteries in our own galactic backyard, the ancient globular clusters. These magnificent spherical swarms of hundreds of thousands of stars are some of the oldest structures we can observe, with ages dating back to within a billion years of the Big Bang. They represent a mode of star formation that was incredibly efficient, turning a vast amount of gas into stars in a very short period. It's possible that the very first star clusters were the primordial precursors to these ancient systems. The first clusters would have been much smaller and composed of only massive stars, but the physical process, a coordinated, rapid collapse of a dense gas cloud, may have been the same. Over time, as the universe became enriched with metals, this process could have scaled up, producing the massive, enduring globular clusters we see today. The first clusters themselves would not have survived. Their massive stars would have died in supernova within a few million years, likely dissolving the gravitational bonds that held them together. But they established a blueprint, a proven method for the universe to build stellar communities that would be refined and repeated for billions of years, setting the stage for the complex galactic ecosystems we observe now. Now we arrive at a mystery that acts as a cosmic fingerprint, a chemical signature left behind by the frantic construction of the early universe. This is the puzzle of galaxy metallicity scaling relations. In the modern cosmos, astronomers have discovered a surprisingly tight and predictable relationship between a galaxy's mass and its metallicity, the abundance of elements heavier than hydrogen and helium within it. Simply put, bigger galaxies are richer in metals. This makes intuitive sense. A more massive galaxy has a stronger gravitational pull, allowing it to more easily hold onto the heavy elements forged in its supernova. When a star explodes in a large galaxy, the enriched debris might be blown around, but it's unlikely to achieve the escape velocity needed to break free from the galaxy's deep gravitational well. In a small, low-mass galaxy with much weaker gravity, that same supernova explosion can easily blow all the newly minted metals clear out into intergalactic space, effectively starving itself and future generations of the building blocks for planets and life. This mass-metallicity relation is a cornerstone of our understanding of galactic evolution, a rule that seems to hold true for galaxies across a wide range of sizes and ages. However, when we point our most powerful telescopes back to the cosmic dawn, this neat and orderly relationship begins to fray at the edges, presenting us with startling exceptions that challenge the simple narrative. The James Webb Space Telescope, in its deep observations of the very early universe, has begun to uncover a population of small, faint dwarf galaxies that, according to all expectations, should be extremely metal-poor. Yet their spectral fingerprints tell a different story. These diminutive systems, which should be cosmic paupers, are instead showing signs of being surprisingly enriched, with metallicities that are much higher than the established rulebook says they should be for their modest mass. It's as if we found a tiny, remote village that, by all accounts, should be struggling and impoverished, but instead discovers it's using advanced technology and materials that we'd only expect to find in a massive industrial metropolis. This anomaly forces us to reconsider the entire timeline and mechanism of early chemical enrichment. So how could a small, fragile galaxy become so metal-rich so quickly? One compelling explanation points to an incredibly efficient and violent period of star formation right at the beginning of the galaxy's life. Perhaps these specific dwarfs experienced a single, tremendously intense starburst, a firestorm of star birth that created a huge number of massive stars in a very short period. These stars would have lived their brilliant but short lives and then died in a coordinated wave of supernova. The sheer concentration of these explosions could have created a powerful collective effect. Instead of individual supernova blowing bubbles that vent metal-rich gas out into the void, their combined energy might have created a superwind so powerful that it actually pushed past the fragile gravitational hold of the small galaxy, but not before thoroughly and violently mixing the newly forged metals back into any remaining pockets of pristine gas. This self-pollution event could have enriched the entire interstellar medium of the dwarf galaxy in one fell swoop, after which star formation shut down completely, leaving behind a small, dense, and unexpectedly metal-rich fossil. Another fascinating possibility involves the concept of external enrichment, a form of cosmic inheritance. The early universe was a crowded and chaotic place. These small, metal-rich dwarfs might not have produced all their heavy elements themselves. They could have formed in an environment that was already pre-polluted by a nearby, earlier source. Imagine a truly massive population, 3-star or a dense star cluster in a neighboring protogalaxy that lived and died just a few million years prior. Its supernova would have blasted a wave of enriched material out into the cosmic web. If our small dwarf galaxy happened to be forming right in the path of that expanding metal-rich shockwave, it could have begun its life with a ready-made supply of heavy elements, literally seeding its gas clouds with the products of an earlier, more massive stellar generation. This would give it a head start on metallicity that had nothing to do with its own mass or gravitational strength, instantly breaking the established rule. There's also the potential role of these small galaxies as satellites. A dwarf galaxy orbiting a much larger host could have its chemical history shaped by its massive neighbor. While ram pressure stripping where the host galaxy's halo gas tears away the dwarf's gas often leaves a satellite impoverished, there are more complex interactions. The gravitational tides from a close pass could compress the dwarf's gas, triggering a burst of star formation that produces metals rapidly. Alternatively, the larger galaxy's own powerful winds, venting from its supernova and active black hole, could actually shower the smaller satellite with enriched material, a form of intergalactic pollution that boosts its metallicity from the outside. Each of these scenarios paints a picture of the early universe that is far more interconnected and dynamic than a simple model where each galaxy evolves in isolation according to its mass. The chemical patterns we see are not just a record of what happened inside a galaxy, but a testament to the violent and shared history of an entire region of space, where the lives and deaths of the first stars created a legacy that was inherited by all who came after. Yet as we explore the chemical legacies and clustered births of the first stars, we must now turn our attention to the most powerful and disruptive engines in the early cosmos, the first active galactic nuclei, or AN. This brings us to a mystery that probes the very heart of galactic adolescence. Just how common were these brilliant, violent quasars in the universe's first chapters, and what was their true role in shaping the destiny of the first galaxies? An active galactic nucleus is the intensely luminous core of a galaxy, powered by a supermassive black hole in the midst of a colossal feeding frenzy. As vast quantities of gas, dust, and even stars spiral down into the black hole's gravitational well, the material is compressed and heated to millions of degrees, releasing a blinding flash of radiation that can outshine every star in its host galaxy combined. These are the cosmic lighthouses that guide our view back to the earliest epochs, but their prevalence presents a deep and puzzling inconsistency. When we look out at galaxies in the modern, local universe, we find that only a small fraction, roughly 1 in 100, hosts an active supermassive black hole. The vast majority of these cosmic monsters are dormant, sleeping giants that have exhausted their nearby fuel supply. But when we point our telescopes back to a time when the universe was less than 1 billion years old, the story appears to be dramatically different. The James Webb Space Telescope and other observatories are finding a surprising number of galaxies that show the clear spectroscopic fingerprints of AGN activity-specific emission lines that can only be produced by the searingly hot gas swirling around an accreting black hole. This suggests that in the cosmic dawn, having an active black hole might not have been a rare occurrence but a common, perhaps even universal, phase of a young galaxy's life. Yet it's not quite that simple. For every early galaxy that shows these signs, there are others, seemingly similar in mass and age, that show no evidence of a central engine at all. This inconsistency is the core of the mystery. If the conditions were right for one galaxy to power up a brilliant quasar, why didn't its neighbor? This leads to the captivating idea of the AGN duty cycle. Perhaps every sizable galaxy did indeed host a supermassive black hole that periodically switched on, but these active phases were relatively brief and explosive. In this model, a black hole spends most of its life in a quiet, quiescent state, gathering a reservoir of gas around it. Then, a trigger event, like a major galactic merger or the sudden inflow of gas along a cosmic filament, pushes a vast amount of material over the edge and into the waiting gravitational well. The black hole responds by igniting into a brilliant quasar, a phase that might last for a few tens of millions of years. During this time, it blasts out enough energy to heat or eject the surrounding gas, effectively shutting off its own fuel supply and causing the engine to sputter out and return to dormancy. This on-off cycle could mean that at any given moment in the early universe, we are only seeing a snapshot, a small percentage of galaxies that happen to be in their active phase, while the rest are temporarily quiet. The galaxies that appear silent to our telescopes might simply be between eruptions, their black holes lying in wait for the next delivery of cosmic fuel. But the impact of these active phases extended far beyond the brilliant flash of light. The energy released by an AGN is so immense that it can fundamentally alter the evolution of its entire host galaxy, a process known as AGN feedback. This is where the mystery deepens from a simple census to a question of cosmic influence. Think of a young galaxy as a delicate balance between gravity, which pulls gas in to form stars, and various feedback processes that push gas out. An active black hole adds a monumental new force to this equation. The intense radiation and powerful jets from the AGN can heat the galactic gas, preventing it from cooling and collapsing to form new stars. In more extreme cases, it can drive tremendous winds that physically blow the star-forming gas clear out of the galaxy entirely. This is negative feedback, a form of cosmic self-regulation where the black hole quenches star formation, potentially turning a vibrant, star-forming galaxy into a passive, red and dead elliptical. Yet, there is also a potential positive side to this feedback. The same winds that can clear out a galaxy might also compress clouds of gas in their outskirts, triggering bursts of star formation in a surrounding ring. The energy from the AGN could also prevent the galaxy from growing too large too quickly, maintaining the delicate structures we see today. The great unknown is determining which effect dominated in the early universe. Did AGN feedback primarily act as a destructive force, shutting down galaxy growth, or was it a constructive one, helping to shape and organize galaxies into their modern forms? The answer likely depends on the specific circumstances, the power of the AGN, the mass of the host galaxy, and the amount of gas available. A powerful quasar in a small, low-mass galaxy could have a catastrophic sterilizing effect, while that same quasar in a massive, gas-rich system might merely temper its growth. Unraveling this complex relationship is key to understanding why galaxies look the way they do, and the first AGN were the original architects of this balancing act. their violent eruptions setting the rules for galactic evolution that would last for billions of years. And so we arrive at the final, all-encompassing mystery that ties together nearly every thread we've explored, the end of the epoch of reionization. We know this grand transition happened. The universe transformed from that pervasive fog of neutral hydrogen into the transparent expanse we see today. But the precise cause of its completion remains one of the most heated debates in modern cosmology. Was it the collective ultraviolet glare from countless early galaxies, the cataclysmic deaths of the first massive stars, or the most powerful engines of all, the brilliant quasars? The answer is more than an academic footnote. It's the key to understanding which forces truly dominated and shaped the cosmos during its first billion years. Different lines of observational evidence point us in frustratingly different directions, each building a compelling case for a different hero in this cosmic saga. Studies of the most distant quasars provide one crucial piece of the puzzle. As their light travels through the cosmos to reach us, it passes through vast clouds of intergalactic hydrogen. By analyzing the absorption lines in a quasar's spectrum, specifically looking for the Gunn-Peterson trough, a telltale sign of neutral hydrogen, astronomers can map how much of the universe was still neutral at that quasar's distance. The data from these cosmic lighthouses suggests that the process was largely complete by the time the universe was around 950 million years old, but it also shows that the process was incredibly patchy. Some lines of sight were almost completely clear, while others showed significant remaining pockets of fog. This inconsistency suggests that reionization wasn't a uniform, rising tide but a chaotic process of overlapping bubbles, and the sources that created the largest, most powerful bubbles would have been the ones to ultimately connect and finish the job. This is where the case for quasars becomes so compelling. A single quasar, powered by a supermassive black hole, is an ionizing powerhouse of almost unimaginable intensity. Its radiation is so energetic and focused that it can carve out a massive Stromgren sphere in the neutral hydrogen, creating a huge, transparent region around it. If quasars were common enough in the early universe, they could have been the primary drivers, efficiently burning through the fog with their focused beams of energy. However, census data from telescopes like James Webb suggests that fully formed, bright quasars were actually quite rare at these early times. While incredibly powerful individually, there simply may not have been enough of them to account for the global completion of reionization on their own. They were likely the precision tools, carving out the largest individual bubbles, but perhaps not providing the blanket coverage needed. This leads many scientists to point the finger at the collective effort of early galaxies. While a single dwarf galaxy might only create a small ionized bubble, their numbers were potentially immense. The latest deep field images from Webb reveal a universe that was far more crowded with small, faint galaxies at high redshifts than we ever anticipated. The combined ultraviolet output from the millions of hot, massive stars within these countless dwarf galaxies could have provided a pervasive, steady background of ionizing radiation, like countless tiny LEDs slowly lighting up a massive room. The appeal of this galaxy-dominated model is its democratic nature. It doesn't require rare, exotic objects, just a universe teeming with stellar nurseries. The challenge here is the escape fraction. For a galaxy to contribute to reionization, the energetic UV photons produced by its stars must actually escape the galaxy itself. If they are absorbed by local gas and dust within their birth galaxy, they're useless for the task of clearing the intergalactic medium. Measuring this escape fraction in the earliest galaxies is incredibly difficult, and estimates vary wildly, leaving a crucial variable in the equation frustratingly uncertain. Perhaps the most intriguing possibility is that no single source was responsible, but that it was a coordinated effort that changed over time. This hybrid model is gaining traction. In the very earliest stages, the first massive population 3 stars, though few in number, might have punched the first initial holes in the darkness. As structure grew, countless dwarf galaxies took over, their combined output steadily expanding these bubbles. Finally, the first quasars switched on, and their incredible power served to blow out the last remaining walls between the bubbles and ionize the most stubborn, dense pockets of neutral hydrogen that the stellar radiation couldn't penetrate. The timeline of reionization end, therefore, becomes a history book of cosmic power. If it ended early, it suggests the dominant sources were incredibly efficient, like quasars or extremely bright galaxies with high escape fractions. If it ended later, it points toward a more gradual process led by the accumulating effort of more ordinary galaxies. By piecing together this timeline with ever more precise observations, we are not just learning how the universe became transparent. We are taking a census of its earliest inhabitants and finally understanding which of them truly had the power to illuminate all of creation. As we've journeyed through these 30 profound mysteries, it's become undeniably clear that the era of the first stars and galaxies represents far more than a simple chapter in our cosmic history. It is the foundational epoch where the basic rules of our universe were tested, written, and ultimately set into motion. Each mystery we've explored, from the silent darkness of the cosmic dawn to the violent feedback of the first supernova, from the enigmatic birth of supermassive black holes to the gritty emergence of the first dust grains, is not an isolated puzzle. They are all interconnected threads in a grand tapestry, each one pulling on the others, revealing a story of breathtaking complexity and beautiful chaos. This isn't just ancient history, it is the very origin story of everything we see and are. The iron in our blood, the calcium in our bones, the silicon in the ground beneath our feet, all of it was forged in the hearts of those first massive stars and scattered across the cosmos by their spectacular deaths. Understanding these pioneers is therefore the ultimate act of self-discovery, a quest to trace our own lineage back to the very beginning of time. The questions that remain are not merely academic, they strike at the core of our existence. Was the transition from darkness to light a gradual process or a series of brilliant, catastrophic explosions? Did galaxies form their black holes, or was it the other way around? The answers will rewrite the textbooks of cosmology, astronomy, and perhaps even fundamental physics. We stand today on the precipice of a new golden age of discovery, armed with tools of unimaginable power. The James Webb Space Telescope is already peering back into this forgotten era, its infrared eyes capturing the faint, redshifted light of the first galaxies and quasars, providing data that is both confirming our theories and shattering them in equal measure. But the journey is far from over. Next-generation instruments like the Vera-C Rubin Observatory will scan the entire sky, uncovering millions of new galactic building blocks, while gravitational wave observatories may one day detect the echoes of the first black hole mergers. The Square Kilometre Array radio telescope will attempt to finally hear the faint whisper of neutral hydrogen from the cosmic dawn, potentially settling the debate sparked by the controversial edges detection. We are no longer just passive observers of the cosmos. We are active explorers, using these incredible machines to conduct a forensic investigation into the universe's deepest past. The thrilling part is that this story is still being written, not in the distant heavens, but in the collaborative efforts of scientists around the world. Each new observation, each computer simulation that better replicates the clumpy structures of early galaxies, each spectral line that reveals the chemistry of a 13-billion-year-old star, these are all pieces of the puzzle falling into place. The solutions to these 30 mysteries will not arrive all at once, but through a slow and steady accumulation of evidence, a process of trial and error that is the very heart of the scientific endeavor. It is a humbling reminder that our understanding of the cosmos is always evolving, always improving, and that the greatest discoveries are often the ones we haven't even thought to question yet. So we leave you with this thought. The next time you look up at a dark, starry night, remember that you are not just looking at points of light. You are looking back in time, seeing the descendants of those first cosmic pioneers. You are witnessing the final result of a journey that began in absolute darkness, a chain of events set in motion by the first star that ever shone. Which of these mysteries captures your imagination the most? Is it the possibility of finding a still shining population 3-star, a living fossil from the dawn of time? Or is it the terrifying power of the first quasars capable of shaping entire galaxies? Share your thoughts in the comments below. We are genuinely fascinated to hear which cosmic question resonates with you. If this journey through the universe's greatest secrets sparked your curiosity, please subscribe for more deep dives into the wonders of space.